Okay, so now we have the two different data frames, and now let's bring those together. So this is a regular join, so we're joining on the day of the week, right? We have day of the week data for mobile, we have day of the week data for desktop. We want to join on the day of the week and bring these together, so we'll take mobile and we'll do a .join against desktop. And the join condition is going to say we want to join where the mobile view's day column matches the desktop view's day column. And again, just to make this extra clear, this join condition, right? This is also a column, right? So, and this, if you're used to R, this will all make, this is all probably like super familiar. But what we're doing here, right? This is a column. That's actually a method on the column. It takes another column and returns a column. So it looks like we've got some special magical expression DSL going on here, but it's actually a lot less magical than it looks. It's just using some kind of overloads or specially defined methods. So now we've got this join table, so we could go ahead and switch to a line chart. So we'll go line chart here. Well, we've only got one series, and it looks like something's kind of messed up, so we'll click on plot options and rearrange this. So it looks like we've got duplicate key here. We only need day once. We'll get rid of that. And we can just drag and drop the mobile requests over there, and now we've got our nice line chart. So, okay, well, we can definitely see what's going on in terms of mobile versus desktop. And then this looks really low, but notice that it's kind of scaled where 600 million is at the bottom. So I know there's a lot of debate in kind of the data community over these kind of charts, but that's what's going on here. So if you want, you'll have access to all of this for some time after class. You can hop in and play with this data set and try out some other operations and graphing. And you can actually use some of the same tools in here to bring in other data sets from outside. So if you want, you can absolutely import other data. And as long as the data sets you bring in are not so large that you can't crunch them with the relatively modest sized clusters here, there's nothing stopping you from bringing in other data into this environment and trying this kind of thing out on your own. Okay, well, what I'm going to do now is I'm going to switch over to the slide deck, and we have a couple of slides that are catching up on some APIs, but we'll talk about the execution, which is probably one of the most interesting parts here, in just a minute or two. So we saw as, or alias, so in Python alias, because as is a keyword, so you're going to be using alias in the Python version. In SQL, of course, you can do as on a column. We've done some group bys along the way. I guess one thing to point out, it may not be obvious with these expressions that we've been playing with that are kind of pre-built examples, but when you start playing with this, you'll notice that there's a handful of objects that you're dealing with in data frames. You've got the data frame itself. You've got these column objects. The other thing is a thing called a grouped data object. So when you take a data frame and you do group by, what you get is actually not a data frame. So you can't do data frame things on the result of that. It's something that's neither a data frame nor a column. It's something called a grouped data object. From the grouped data object, you can then do other operations. So in this case, group by age produces a grouped data, and then calling count on that actually gets you back to a data frame. So SQL group by has been around for quite a long time, and it's not changed. We saw an example of a join in the end of the last lab. So there's a couple of slides showing examples of a join. So here's a join. This is basically what we just did. We had a data frame. We did a join onto a second data frame, and we specified a join condition here. And in here, we're projecting out only some of the columns. And we saw an example of a user-defined function. So we have that example, but if you want to go back to the slides and look at some sort of more straightforward documentation on that, you can see some examples of how this works. So we wrote a function, and then we called UDF on our Python function object. In this example, they're doing it inline, so you can certainly say UDF and then pass a lambda. And this is kind of like a mapping operation, because this operates on each row within a particular column. In Spark 1.5, there's actually an API that's not in this slide deck for user-defined aggregation functions, right? So these user-defined functions we're talking about, they're kind of like map functions because they operate on each row independently. If you want to create an aggregation that's different from the built-in ones, that's a little more complicated because that's essentially a reduce. So you effectively need to implement all of the pieces that one needs in order to do a reduce. So that's a little more complicated, but I wanted to make sure that you were aware that in 1.5 there is an API for user-defined aggregation functions. And when you're interoperating with Hive, you can also use the UDFs and UDAFs that are defined in Hive if you've got a Hive setup that has these things defined. So this is highlighting the register temp table feature. We haven't done any SQL in our labs, so in the notebook we were doing pure data frames API. A lot of times you might want to write SQL. If you want to do that, we can just take a quick look at something like that. So if I have my, let's see, desktop views by day of week. So if I come in here and I say something like register temp table, now I can issue SQL against that. And we get back out a data frame, right? So if I issue a SQL command, I get back out a data frame. I could take this and do like a .show and get stuff like this. So the SQL, of course, is not that interesting, but this shows how we can go from data frames into the SQL world, and then we come back out into data frames, and they're basically the same thing. There's different ways of talking to it. So, okay, we said we're going to talk a little about execution and performance. So one of the motivations for data frames was to have this API that would be familiar to people who are used to other systems, and that's great. We also said that we would get some performance benefits. Right, so one of the things, there's two things to notice here. So first is that regardless of what language you're using with the data frame API, you get the same performance. Right, so when working with RDDs, Python runs slower than Scala, and it's for the reason that we mentioned earlier that your Python code is running in a real Python VM, which means that it needs to be marshaled, well, not really marshaled, but moved between the Java VM and the Python VM. Right, and in the Scala world, we don't have to do that. But it turns out that with the data frame API, we're going to get the same performance. And that's because the code that's running underneath is not actually the code you're writing. We're going to see where the code comes from. So regardless of how we write it, we're going to get the same performance. And this performance is actually faster even than writing native RDD code in Scala. Now, depending on the job you're doing, I'm not saying that you'll necessarily get this same, here it looks sort of to your eye as if it's sort of 50% of the time or twice as fast as doing it with RDD code in Scala. That may not always be the case, so that's not the point of the slide. The point of the slide is to say, one, it doesn't matter what language you use, and two, your performance should be at least as good, and in many cases, maybe significantly better than what you get by handwriting RDD code. Right? So here's why. We said that with RDD code, there are some optimizations Spark will do, and we still haven't talked about those. That's the next section we're going to talk about. But we said that certain things like when we did the filter and the sort, we said Spark's not going to reorder those for you. If you put a bunch of sorts in the wrong place, it's going to cost you, and Spark won't be able to undo that for you. When we're doing operations with data frames, there's an engine called Catalyst. Catalyst is kind of a product name, I guess, so I'm not sure how important that is, but it's maybe good for doing searches online. And Catalyst is the engine that can optimize the queries that you're submitting. So here, we'll look through an example of this, and we'll talk about that flow here. So if I feed in SQL, like in the example I just did in the notebook, where I had sort of a table name, and I did a SQL context.SQL. If I feed that in, it's going to run through a SQL parser and generate a SQL AST over here. And if I write data frames code like we did throughout the lab, I will get some data frame code here. And when I do these operations like select and filter, what I'm doing is contributing to a query plan. And at the end of that, when I actually call some kind of an action, this is the process that Spark is going to go through. So we start with this unresolved logical plan. Unresolved logical plan means we have a brute force model for doing the query, and we don't even know if all the stuff that's in that query, if we can find that somewhere. We don't even know if it all exists. So an example would be a SQL query that we pass in as a string, and I select from some table that I just made up, right? So the SQL parser can parse that, but the stuff that I made up, we're going to run into a problem here. So the next thing that's going to happen is Spark is going to look at this catalog and say, let me match actual objects I know about to the entities that have been specified in this query. Right? So that's where register temp table helps out. So when I did a register temp table, that was so when we get to this phase of analyzing the query, we can match the data frame that I registered against the actual string. So against this token in the string. Right? Because this token, in order for this token to have meaning, we need to have basically put an entry in the catalog somewhere, and that's what this does. Okay, so if we can't resolve those things, then we're going to bail out. You'll get errors, right? So even though it looks like we're writing SQL as a string, Spark is, as soon as it gets to this point, if it can't resolve these or the types don't make sense, we'll error out. If we get past this stage, then we get to logical plan. So logical plan means we know all of the functions and pieces of data that we're dealing with, and we've got a brute force process to do it. So the next thing is getting from logical plan to optimized logical plan. So here's where Catalyst comes in. So Catalyst is a really neat piece of code, and there's a white paper. I have a link to it in a couple of slides, or if you skip ahead, if you've got the slide deck, you can see that. Not the whole paper, of course, just the link. But what it does is it's a model for describing optimizations that can be done locally based on places in an AST representing the query. And the idea is that if you can describe a local optimization, and I'll show an example of this in a second, so I know this is fairly abstract, but if I can describe a local optimization, I can let Spark implement that optimization everywhere throughout the whole tree, and maybe even apply that more than once to get the most optimized version of the tree. So again, if that sounds too abstract, we'll see an actual example of it. But it's a really neat algorithm and implementation. So it takes a collection, so that's a model for applying optimization. So where do the optimizations come from? Well, there's a handful of built-in optimizations, and you could also write your own if you want. So we take the bunch of built-in optimizations, and we run them against the tree that represents the query, and then we run them again, and we basically keep running these operations throughout the tree until the tree settles and reaches a fixed point. Right? So at a certain point, we'll have a tree that is no longer optimizable by these operations, and that's the optimized logical plan. Okay, so that gets us to this piece here. Now we can go a level better, which is there may be more than one physical plan that can be used to execute this. And if you're used to the way databases do query optimizations, you're probably familiar with a lot of these ideas. So a couple of physical plan versions. One is, what if some of my data sources can actually do some of the operations in my query? So sometimes this is referred to as things like predicate pushdown. Right? If I'm reading from a data source that knows how to do a filter, I don't need to load all the data and then do a filter in code. Right? I can move that filter down into the underlying source. Right? So that's a physical optimization. Another optimization is in Spark, there's a way of sharing data using a BitTorrent-like protocol across a whole cluster. We haven't talked about it. We're not going to do that because this class is too short. But it's called a broadcast variable. So if we're joining two tables, or one of those, or data frames, if we're joining two data frames and one of those sources is below a certain size threshold, the planner will say, instead of doing these both as distributed data sets, why don't I take the smaller one and broadcast it? Right? So that's a physical alternative that will yield performance benefits. So there's different physical plans, and then what we do is figure out, well, which of these physical plans is the cheapest to execute. We pick one, and then that becomes a set of RDDs. Right? So we generate, once we've gotten to this phase, we generate a set of RDDs and a DAG. And actually, this isn't even really the end of the story because we have a little bit more that comes on here. So when we get to the RDD and DAG phase of this, first of all, when we generate code using data frames, We don't generate all of the different APIs that humans might use to program against RDDs. The planner here generates operations that boil down to just 3 operations. I think they're map partitions, zip partitions for joins, and new shuffled RDD, which is for things that involve moving data between partitions. So those are maybe too deep in the weeds, but the idea is that by essentially compiling this down to a small number of primitive operations against RDDs, we can focus on optimizing those, and then we can code gen for those. So from those operations, we actually generate code, so we're running compiled Java bytecode at the end of the day. Right, so when we get to that point, we're not running operations in interpretive mode as if we were doing it step by step. We're actually generating code for this. So at that point, we've got a fairly optimized set of operations to do, and that's where these performance gains come from. Right, so the equivalence of the languages comes from the stuff at the left-hand side of this picture. The fact that whatever language we use to walk into this, it all just becomes a logical plan internally at this point. So that's why the languages are equivalent. And the reason why the code here is faster than handwritten code and faster than RDD code is because when we get down here, we're dealing with a limited subset of RDD operations that are optimized and are then getting code or then performing code gen. So let's look at an example, because I know that especially the stuff about Catalyst was a little bit up there, maybe not quite on the level of Handwave, but maybe a little bit too high. So let's just take a look at a simple example of this. So let's say we have 2 data frames, so one called users and one called events, right? And so they have some IDs, and we'd like to join these and then pull out some items. So we're going to say take the users and join against events, where the user's ID matches the events.uid. So it's like a foreign key kind of idea, right? So this gives us a joined data frame. And then we'd like to pick out the events from that collection that are after January 1st of this year. So we're going to say join.filter events.date greater than or equal to this date string. Okay, so simple enough. So the brute force logical plan looks like this, right? Events scan, users scan, do some join, do some filter, get some answer. Right? But that join is expensive. And if you look at this, you know as a human, or if you were trying to hand tune this, you'd say, well, why join all this data and then throw most of it away, or even throw some of it away, right? Why don't we filter before we do the join, right? It turns out that in many, many cases, you can move the filter down below a projection or below a join, right? So those are exactly the kind of examples of optimizations, local optimizations that are part of Catalyst, right? So there's an optimization rule in Catalyst that says, like, if the local shape of the AST has these characteristics, we can move the filter down below the join or down below a projection, something like that, right? So we'll get an optimized plan like this, right? We could say, okay, let's just go and let's move the join up and move the filter down, right? And we could even have rules that try to decide, well, where do we move the filter to, or can we duplicate the filter? What do we do there, right? So here's an example of an optimization being applied to get us to an optimized plan. And now we can bring in the physical planning part. So here's the original brute force logical plan. Here's the optimized logical plan. And now we can say, well, maybe we've got some physical alternatives. If we're reading from, say, an RDBMS, well, we can do a filtered scan or maybe some other kind of read. We don't need to do this in memory. We can, in our own program, we can have the RDBMS do this. In the big data world, we often see this with Parquet files, right? So we highly recommend using Parquet files to store your data because Parquet files can do this. So Parquet files have schema information. They also can separate by column, and they can separate by range. So Parquet files can allow you to read only the part of the file, in the best case, only the records that you're interested in. It's probably not exact all of the time. But we can certainly discard a lot of the data without ever getting it off the disk, right? That's the beauty of Parquet. So that would be another situation where we could push this predicate down. We can push the filter down into the Parquet reader. If we want to see how Catalyst is thinking about our query, we can call explain on a data frame. Now, you might say, well, that sounds kind of weird. I mean, the data frame is a thing. How can we do explain on it? Well, but remember that when we assign something to a variable and we call it a data frame, that's the metadata, but it hasn't been materialized yet. So when we say df3.explain here, what we're asking is, if you were to materialize df3 right now, how would you do it, right? And if we say df3.explain, it's like doing explain in a SQL database. So you'll get a query plan. So here we can see there's some different steps in here. And this is actually the shorthand version. If you want to see the full plan, you can call explain and pass true, and you'll get something like this, right? So at the very top, we're saying, join df join df2 on first name from the one matching first name from the other, lower applied to both. So it's basically a join normalizing the data in this one column. And we say explain true, and we get out sections that correspond to that diagram I just showed, right? So parsed logical plan, this is what it looks like. Analyzed logical plan. So notice we can track this conversation we just had through the different stages here. So parsed logical plan. Analyzed logical plan looks about the same, except that now we've brought in the catalog information. We know what all the different types are. Optimized logical plan. Well, in this case, the optimized logical plan actually looks quite a bit like the analyzed logical plan. So I'm not sure we're seeing any, I have to squint at this pretty hard. I'm not sure I'm seeing a lot of optimizations there. But in many cases, you'll see optimizations going between these two. And then the physical plan. So how is this actually going to be converted into RDDs? There's also some visualization in the Spark UI. We haven't played with the Spark UI yet, but we'll do that in the next section. There are visualizations where you can see the query planning kind of visually. So this is just a screenshot of a blog post about Catalyst. The link at the very bottom goes to the blog post. From there, you can get to the paper on Catalyst. If you're interested in this sort of thing, I recommend the paper. It's not very long. It's really neat. It's definitely worth the time if this is the kind of thing that you find interesting. A couple miscellaneous notes on data frames. So currently, Catalyst doesn't automatically repartition data frames. So there's a configuration value that describes the number of partitions that's involved for data frame operations, and currently it kind of stays that way. That may change in the future, where that may adaptively repartition. But I don't want to promise anything that's not actually done. And if you want to change configuration values, you can actually do that dynamically by calling an API like this. So we'll talk more about machine learning towards the end of the day. This is not a section on machine learning. The reason it's here is because in the, I guess somewhere around 1.4, I hesitate because APIs sort of come in over time, like little bits, and then bigger and bigger. But there's definitely a wider and wider deployment in 1.4 and 1.5 of an API called Spark ML or ML pipelines. And that's about integrating machine learning algorithms and data kind of cleansing and transformation and preparation into data frames. So it becomes kind of a unified API. I can give you an example of that towards the end of the day. But the idea is to have a data frame where we take our initial data, and then as we process our data into input for machine learning algorithms, we're adding on columns into a data frame. And we apply machine learning algorithms to certain columns and say, OK, train on this column and then operate on this column, or make predictions on this column and output to another column. So it's an integration of machine learning algorithms with data frames. So we'll talk a little bit more about that later. But basically, it's a way of integrating data frames as a model for storing all of that data. And it makes certain operations like hyperparameter grid search easier because they're kind of built in. But we'll talk about that later on. So let's see where we are here. Okay, well, I think we're in a great place now to dive into the Spark execution, right? So with the Catalyst stuff that we just talked about, we talked a little bit about how data frames break down to be executed. And at the end of the day, we still ended up with RDD operations, right? So somewhat optimized, but RDD operations. So now we want to sort of take that panel off and look underneath a little bit about how Spark actually executes stuff. When we give some command like .collect or .sum, or we materialize something from a data frame, how does that run? So this is a quote from Patrick Wendell, who's one of the Databricks founders and is a committer on Spark. The key to tuning Spark apps is a sound grasp of Spark's internal mechanisms. And so why do I mention this? Because knowing how Spark operates under the hood, it's not just about being intellectually curious and understanding the technology, but it's key to actually getting jobs that perform really well. Right? Theoretically, we'd love to get to a point someday where everything just auto-magically tunes itself, but I think that's one of those things that will never be completely there. And so it's really useful to understand what's happening when we run one of these jobs so that we can arrange our code in a way that'll perform well. So I'm going to start with kind of a high-level description of these terms, and then we'll dig down into exactly what they mean. So when we say job, what we mean is the work required to compute the result of some action. So if I have an RDD and I say .collect, that's an action, it spawns a job. Generally speaking, an action will spawn a job. There are some actions that can spawn more than one, so it's not exactly a one-to-one correspondence, but generally, running an action is going to spawn a job in Spark. A stage, well, there's again a more technical definition of stage, but for now we can think of a stage as being a wave of work within a job corresponding to one or more pipelined RDDs. A task is a unit of work within a stage corresponding to a single RDD partition. So you might remember from earlier this morning, there was one slide that showed partitions, and then we said if we're running a certain kinds of operations, like a filter, we're taking one partition, filtering, and producing one partition. And so we're running those in parallel. So each of those is a task. So one partition and an operation will produce one task. And the shuffle is the transfer of data between stages. Right? So, and the shuffle and stage are kind of mutually dependent definitions. You can say a stage is the part of the job separated by a shuffle, or the shuffle is the transfer of data between stages. So where does this shuffle come in? Well, not every operation can be done strictly in parallel, right? All the stuff we're doing would be vastly easier if we could magically just do everything in parallel, right? So we can do some things in parallel, but sooner or later we need to move things across between partitions, right? Earlier we did a sort. As soon as you do a sort, things have to move, unless they were sorted to begin with, in which case it's not that interesting, right? So if we want to sort our data set, we need to move things between partitions. So that's the shuffle, and that's the really expensive operation when we're doing these data processing tasks. And the reason it's expensive is we need to communicate between machines, we need to read and write from disk, right? We can't just do this in a totally parallel way. So we've created dependencies both between different pieces of logic and also across our cluster of machines, right? And so both of those are expensive. So to understand how Spark breaks jobs down into stages and tasks, we need to understand a little bit more about transformations. So we said at a high level, a transformation is anything that takes an RDD and produces another RDD. But within transformations, we think of them as being in two groups, narrow versus wide transformations. So a narrow transformation is the kind that we described when we looked at filter, the kind where the output, where each partition of the parent only goes to one partition of the output. So the outputs can all be done completely in parallel. Right? So if we think about taking our log lines RDD from this morning and applying a filter to it, right, there's no dependency between the data in any of those partitions. So from each parent partition, we know right up front that we can apply that filter operation and produce just a single child. We don't care what's happening in any of the other child partitions. Right? So map and filter are examples of narrow partitions. There are a couple of other examples of narrow partitions which are not as immediately intuitive, but if we think about it, we can see how that works. So for example, if we ask Spark to do a union on two data frames, I've been talking about data frames for so long, RDDs, if we ask Spark to do a union on two RDDs, well, we could move data between partitions, but we don't have to. We could just take the partitions from this RDD and the partitions from that RDD and call it another RDD, right? So we can do a union as a narrow RDD if we do it this way, right? So we don't actually move data from a parent partition into more than one child. Some joins can also be narrow transformations. So if we think we're doing a join, typically we think that we probably need to move a lot of data across or back and forth. And in many, many cases that's true. But there are some cases where it's not, and being aware of that will help us optimize our jobs. So if our input RDDs here, the blue ones, if those are co-partitioned, right, if they're partitioned the same way, then we could do a join that's actually narrow because we know that the data from this partition here won't have to go to it'll only have to go to one child partition, right? And it'll be mated up with the data from the similarly numbered partition in the joined RDD, right? So if we number them from the top, right, this is sort of RDD1 partition 0 and RDD2 partition 0. Those guys they don't produce data that ends up in the child partition, in the child RDD in any partitions besides 0. So this is actually a narrow transformation. Now, how would the initial inputs be co-partitioned? Well, for example, if we had started with one piece of data and then we had, say, mapped them around in various ways, but without changing them a whole lot, or if we had intentionally sorted them at a certain point. So there's a lot of ways we might have a situation where they're co-partitioned. What about wide transformations? So wide transformations are the ones where we definitely need to move data from at least one parent partition into multiple child partitions. So something like group by key, right? So the data items with a particular key, they could be anywhere in this initial data set. So they could be in more than one place. And each of these partitions in the parent might contain keys that are destined for more than one child. Right? So in this first partition 0 up here, there might be keys that are going to end up partitioned into these other partitions down here. So from a single parent, we're going to potentially multiple children. And lots of operations like reduce and sort all will involve a shuffle like this. And down below, we have an example of a join where the inputs are not co-partitioned. So this version on the left, this is kind of a special case. It's kind of the edge case that we would like to have that will represent better performance when we can manage it. But if we just do a brute force join and we don't have this co-partitioning, well, we don't know where these values are destined to end up, so it may very well be the case that there are data items in partition 0 up here that will end up needing to go into more than one partition down here. So narrow dependencies never involve a shuffle. Wide dependencies may involve a shuffle. So now we can actually drill a layer down into this job stages tasks terminology and figure out how this works. So our application that we're running in the driver, which is the only place where we can actually talk about RDDs and try to run operations against RDDs. Right? You can't actually talk about RDDs or do things to them out on the executors. If you try that, you'll get a really nice error message explaining that you can't do that. So the data and the various lambdas are running out in the executors, but the control code, the structure of the operations that we're running, that's running in the driver. So we have this application, and we call an action like, say, collect, and that becomes a job. And what Spark is going to do is break that job down into stages based on shuffle boundaries. So it's going to look at the DAG, this directed acyclic graph of RDDs, and it's going to figure out where there are shuffles based on which transformations are narrow versus which ones are wide. And then once it's figured out where the stage boundaries are, those are kind of the limits on what can be done strictly in parallel. So then within the stage, it will create tasks to process each partition. So the application in the driver will launch a job, and the job will become stages. And here we've got a slightly dense slide, but this kind of brings it all into one nice picture. Right, so we have something here like, say, we've got an RDD, we're joining, we're doing a group by and a filter. So we've got a DAG of operations over here. And when we go to run this job, we're going to pass the DAG to the DAG scheduler. And the DAG scheduler's job is to locate these stage boundaries and to break this thing up, right? So the DAG scheduler says, okay, well, I've got a wide transformation here. I'm going to break this thing right here. Boom. So now I've got some stage over here, I got some other stage over there, right? Once we've got it decomposed into stages, we can say, oh, okay, well, let's take a look at the first stage that we need And let's take this set of tasks and pass it over to the task scheduler. And then the task scheduler will launch those tasks. And remember, a task is an operation against data in one partition. And it will launch that onto some, to use some slot in one of the executors. Right? So this will run on one core in one executor somewhere in the cluster. So we start with the job. We break it into stages by finding the shuffle boundaries, so the wide transformation shuffle boundaries. We then find the earliest stages we can execute. So in a lot of DAGs, there may just be one stage we have to do first before we can do subsequent ones. But we can also have a situation where we can run more than one stage in parallel. So let's say we're reading from HDFS over here and reading from Kafka over there. Right, so those two things, they could be stages that are maybe being done in parallel. And at some point, maybe we need to bring that data together, so we may not have complete parallelism too far down. But once we've got it narrowed down to a stage, we can figure out the tasks within that stage, and then we can schedule those. So let's take a look at an example, and then we'll maybe add a couple more notes to how this works. So what are we doing here? So this is a program that's counting what kinds of log messages we get. So it's kind of a word count, but it's not counting all the words in our log data here. It's just looking at these things, info versus warn versus error. Right? So let's say this is our program. So we do a text file on some log file. We do a line.split on the spaces. We filter out empty lines. And then we map from the words to, and words is really a line here. So we're mapping from a line to the first word in a line. This is actually Scala code. I didn't port this one to Python. We're mapping from the line to the first word in the line and a 1 as a key value pair. And then we're doing a reduce by key. So for each of those head words or initial words, we want to sum up all the ones. Right? So this basically your traditional word count, but where we're counting just the first word. So okay, so we submit this when we do a reduce by key, and we want to get something out of here. So we feed this in, and what does Spark do? Well, Spark doesn't worry about the lambdas or the parameters here just yet, because we're trying to just determine the structure of the DAG. So we'll just blank all that out, and we'll look at the structure here. So if we ignore the parameters and we look at the structure of this, what does it look like? So text file goes to map, goes to filter, goes to map, goes to reduce by key. Right? So this is kind of an abstracted version of this. Now we know that reduce by key is what we're going to have at the end here. And remember we said that we write the code kind of thinking about the data flowing forward, like from a text file, then we filter it, then we count it. But the way Spark does it is it just gathers all that together and then it works its way backwards. So it's actually going to say, well, reduce by key, that's the thing that I need. So that's going to be a shuffled RDD that's going to be coming from some other RDD. And I'm going to need this map RDD for that. And that map RDD is going to be coming from a filtered RDD. And that's going to be coming from another mapped RDD, and that's going to be coming from this Hadoop RDD, which is the Hadoop reader is used to read the text files. So we've got something like this, and we'll know how many partitions we have. So there's rules for the parallelism of these things. So for example, with HDFS, when we read data in, we get a partition per block. And then in order to actually do this, we're going to run this run job method on the Spark context here. So we don't write this code. I mean, as end users, we don't, but this is internally what's going on. So this is the Scala function signature for run job. And what does it take as parameters? Well, we need to know what RDD we're trying to compute, which partitions that we want to compute, and we need to know what function to actually run on that to produce the results. And this is supposed to produce the results for each partition. Right? So we're basically going to recurse all the way back. So we need the target, we need the target's parents, we need the parents' parents, and so we'll work our way all the way back. So here we can see, well, here's the shuffle, right? So the reduce by key involves moving things between partitions. So this is a wide transformation, and it's going to require a shuffle at this point. So the scheduler says, okay, well, this is a stage boundary. right? I've got a shuffle here. I can't do parallelism kind of across the shuffle boundary. So I'm going to break this into two stages. We've got the downstream stage here, and then we've got the upstream stage, which is this thing over here. Now over here, this is all nice and parallel. So this is the optimization we're going to talk about now, is the optimization that Spark will do for you. So within a stage, Spark will do what's called pipelining. So pipelining is where we say, well, look, we've got these series of operations, these series of tasks, or sort of notional tasks, that can all be done in parallel with no other dependencies. Let's combine these operations into a single task. So in fact, in this stage here, we won't have a task for all these yellow arrows. We'll actually just have a task for each partition, right? So the mapping, filtering, and mapping are all going to go on together in a single task, and then we'll have another one for partition 2 and another one for partition 3. So that's what's referred to as pipelining, so that within a stage, we combine the operations for each partition into a single task. And that's kind of nice because it means that we're not paying a huge price if we write code. So you might, let's say you have like 3 filter operations in a row. And you might think, well, maybe I should combine this into one really complicated filter. Well, it might save you a couple of cycles, maybe, but it's not going to make a big difference. Because if you have 3 filters in a row, right, those are all narrow transformations. It means those operations can be pipelined. And so the filter will become just one task anyway. So it's not actually going to do these as separate operations if you have narrow transformations in a row. So we'll get our pipelined stuff over here, and it's going to look like this, right? So once it's pipelined, we're going to get this picture. Stage 2, not too much we can do over here. Stage 1, so all those operations, right, the map and filter, all combined into a single task in here. And what we're going to do is read from outside the system. We're going to do our task, and then we're going to write our shuffle data. And then in stage 2, we're going to read that shuffle data and put it into the correct partitions downstream. And we'll get our output from there. So that's kind of a brief summary of how Spark actually schedules work. In some of the longer classes, we go into detail about, how does that, that still doesn't tell you physically how the shuffle works, for example, right? Like, where does the stuff get written, and in what format does it get written? And, there's more than one method to doing shuffles that can work differently for the different numbers of partitions. So if in some of the longer courses, we go into exactly how that works. So more details about the shuffle. We could also talk about things like locality, right? Because here we said, once we've got a task, that gets scheduled on some core and some executor on the cluster. But in fact, not all cores on all executors are equal, right? We'd like things like data locality. If we have a task that's, say, filtering certain lines of a file, it would be really nice if that code ran on the machine where that block of the file lived, right? Theoretically, we could put it somewhere else, but we're going to pay a price for that. So there's a system for trying to give locality a certain amount of priority, but not so much priority that it holds up the entire job, right? So that's tunable as well. So there's a little bit more depth underneath here in terms of how this works, but that should give you a general idea of the major levers that you can work with in terms of how many shuffle boundaries do you have, where do the shuffles occur, and how many tasks are you going to have. So let's go and take a look. In this next section here, what I want to do is run a few operations. So we're going to do some really simple code. We'll just do it together. So you can I'll bring up a notebook here, and you can clone it and kind of follow along. And we're going to look at some operations that are really trivial in the code, and we're going to look at the Spark UI. And the Spark UI will show us a lot of this information. So we can see what the DAG looks like. We can see how many tasks there are, and kind of solidify our understanding of, if there's 4, why are there 4 tasks here? Or if we change how many partitions, does that really change how many tasks? So let's take a look at that. So what we want for this is, if you go under today's labs and go to where it says Stages, Architecture, Demo, Python, and clone this notebook. So I'm going to make a copy over My copy is in my home directory here. And the stuff we're doing in this lab, content-wise, it's really simple, because the point here is not to do really complex work. It's to understand how the work is being executed. So what we want to do is also take a look at the UI. So I'm going to kind of move this over here. And if you make another tab in your browser and go down to clusters, actually, depending on your privileges, you may not be, if you can't get to the clusters page, don't worry about it. There's another way to get to this. So let me know if you can't get to this particular view. And what you're going to do is go down to your own cluster. So I have a cluster here. And where it says View Spark UI, go ahead and open that in a new tab. And I'm going to pull this tab off, and I'm going to put it here so I can try and run these guys side by side. So we're a little tight for space, but I think I can get these to fit. And we'll kind of look at both of these. So here's my notebook on the left. Here's my Spark UI for my cluster. So this top part here with the menu, that's all part of Databricks, but the Spark UI is part of open source Spark. So this is something useful to realize is whether or not you ever use Databricks, the product, the Spark UI is core Spark. If you just spin up Spark on your local machine, this UI will be running on port 4040. You can just point a web browser at it. So this is all part of the core Spark distribution. And there's tons of new features and visualizations being added to this every version. So what we want to do here is take a look at what's going on. So the first tab that you'll notice here, this sort of tab UI, it says jobs. And this lists all of the jobs that I've recently done. So let's go and run a job and see if it shows up in this UI. So before, I'm going to go to the very top of my notebook. Before even the very first cell, I'm going to insert a new cell. So what can I do that's supposed to force a job to show up? If I run an action, that should kick off a job. So let's just make a really primitive action. Let's just parallelize a collection of these two numbers, right? And let's add them up, right? So sum is an action. So let's attach this to my, cluster here, if I can find my cluster. Here we are. Oh, I'm at the top. Okay. So sum is an action. So that should kick off a job. And remember I said there's another way to get to the UI. So you can also go through here. If you expand this out where it says Spark Jobs, you can jump into the UI this way. But what I'm going to do is I'm going to leave the notebook over here. And over here I'm going to refresh. So notice right over here under the description column, that's the exact thing I just put in. Right? So I just ran an action and that launched this job, and it's showing up in the Jobs UI here. So if I click on this link, I can drill down into the UI for that particular job, and I can see some more information about it. So it says completed stages 1, right? So how many stages? Well, there were no shuffles in there, right? So we just have one stage. And this is a visualization of the DAG. It's pretty simple, right? Because all I did was parallelize data from the driver and then sum it up. So I've got a parallel collection RDD, and then Python RDD, and that's it, right? And it's all in one stage. So this red box says stage 225. There's also an event timeline. We're not going to really see much anything on there. And down here, we have a little bit of information. We'll do some more things and look at this in a bit, but you can see that we've got some information about the stage. We can see how long it took. Here at tasks, it says 4 tasks succeeded out of 4 total, right? So there were 4 tasks. So let's investigate that a tiny bit here. Let's come down to this next one. So let's go and do this word list. So this is a regular Python list. So this is word list, has nothing to do with Spark yet. Now let's parallelize this word list. So I say sc.parallelize word list, comma 4. Now we haven't seen this API with the comma 4 before. The comma 4 is how many partitions you want. Right? So if you don't specify, there's a config called Spark default parallelism, and that has a definition for how it derives a value to use here based on how you're running Spark, based on your cluster, if you don't tell it how many partitions to use. But here we can manually say use 4 partitions, And we could say, well, let's go see how many partitions Spark thinks are in words RDD. So we can go words RDD.get num partitions. So it says 4. Now, can we find it in the UI yet? We can't, because we haven't done anything with it. There's no job yet, so nothing's been executed. So we got to run something on this first before we can actually find this in the UI and see what happened. So let's try this next cell. So we're going to define a function called printLine that takes a value, and it just prints the value. Right? So not a very exciting function. We're going to say wordsRDD.map. We're going to pass printLine. Well, this doesn't really do anything because we haven't run an action, right? So we did a map, but there's no action, so it's still not going to do anything. If we refresh over here, you can verify that. If you go back to the Jobs tab, right, the last job that shows up is the one I did before. There's nothing showing up here, right? We just applied a transformation. So let's do something like this. wordsRDD.map using printLine, and we'll do a collect. And we know collect will force something to run, so let's run that. So first, let's see that something actually happened. If we come over here, right, here's our comment, collect. If we click on collect, we can see that in fact there were 4 tasks here. But let's see what happened. So we got back out this thing here, like none, none, none. So what's going on here? It's kind of a weird mapping that I did. Right, so I said I wanted to do a map, and map takes something in and produces something out. But my function here doesn't give us anything out. That's why we got none out, right? This maps everything to none. So that's why the data that comes out is all none. But nothing prints. Where is this going to print? Well, this is going to print on the executors, right? Because the map operation doesn't happen in the driver. It happens on the executors. So if I wanted to actually see this output, I'd have to go and look in the executor logs. Now we can actually go and take a look here. If I go back to the clusters, actually I may need to go into here. Let me locate my cluster. And see where it says logs, right? So I have a shortcut that will get me to the logs here. And if I look in the logs, right, so here's actually the output, right? So that's where the output went. Okay, so this is just, nothing too exciting, but mainly to just give you an opportunity to see for real where are things running and how many operations are there. And let's try asking for a different number of partitions and see if that spawns us the number of tasks we would expect. Right? So if we take the same word list and we put it into 6 partitions, and then we do a collect on there. Now there's only 5 names. So it seems a little silly to have 6 partitions. We know we're going to have an empty partition, or will we? Will we have 5 partitions or 6? Well, let's go take a look. So if we come over here, we can see that we have 6. So just like in that slide deck that we looked at this morning with the RDD fundamentals, it's okay if we have empty partitions. It may not be efficient in terms of using our cluster, but from a formal point of view, that's fine. 6 partitions are 6 partitions. We know at least one of them is empty by some kind of pigeonhole argument. And we get 6 tasks, so a task for each of those. So we can take a look at this Spark context. I think we did this earlier. We said this is the Python handle to the context. And the API on the Spark context lets us do things like check out what version we're running and see what the application name is set to. You can set this to your own application name when you set up your own program. We can also ask for the default parallelism. Right? So the default parallelism is 4. And that explains the 4 that we got down here, right? So when we did this, we didn't specify anything about parallelism, but when we drilled down onto that job, we saw that it was executed as 4 tasks. So now we can see why that is. The default parallelism is set to 4. So if we parallelize a local collection, we're going to get 4 partitions, whether we've got 3 records or 3 billion records. So let's take a look at a slightly larger chunk of data. So this is the Tom Sawyer text from Project Gutenberg. So this isn't really big data, but it's bigger than what we've played with so far. And we can load this up and then do a collect on it, and we're going to get a bunch of lines of text, right? So here's Project Gutenberg, and then we've got some text from the novel here. Now in this case, when we said text file and we passed the parameter 2, right, we can see how that affects the parallelism for that job. So this is the entry for that job. Oh, I've got no data. That's weird. Ah, there we go. So it took a couple seconds to catch up with the output there, maybe. I'm not sure what was going on there. But here we can see that we have 2 tasks. And if we expand this a little, we can start looking at some of the other data that Spark is telling us. And these are all going to give us tools that we can use to understand and tune our jobs. Right? So over here we can see that we read 412K. And we've got no output, we've got no shuffle data in here. So here's where the collapse cell comes in handy. We can shrink that down. Right, so if I take this and I try to do a count on it, this blows up. This is just helping us remind ourselves about how this API works. If we call collect, we get a native collection and we don't get back an RDD. Right, we've got a plain old Python list here. And this is stuff we've talked about before, right? If we do this operation here, we're not going to see anything in the UI yet. We haven't run an action, so we haven't launched a job. If I do a .count, right, now we've actually run a job, and we've got some data out, so now we should see a result from that. Right, so that's this guy over here. And we asked for 2 partitions. We had 2 tasks. We can see there are 2 partitions. That all lines up. Right? So one partition is going to be processed by one task, and that's going to be allocated to run on some one core somewhere in the cluster. And here we can see that we've actually got the RDD back out. So there's a call called glom you can run on RDDs. And what that does is it sort of refactors the RDD so that all of the data in a partition becomes an element. So that it's not always that useful. But one of the things we can do with it is it'll let us visualize what's in the partitions. Right? So if we had 2 partitions before, we expect to get out something that has 2 elements, each of which has all of the data from one of the partitions. Now, printing this out, so the output here shows up, well, there's just too much data to actually make visual sense of this, right? So I'm claiming that we expect to see a list of 2 things, and each of those things will be a list of all the stuff from a partition, but you can't really see that here. So we have a little helper function. So if I scroll down, so here's a helper function, and what this does is we're going to take this RDD, we're going to do this glom on it, and now that returns an RDD, and then we're going to do this thing called zip with index. So what zip with index does is it produces a pair RDD where for each item in the initial RDD, you've got the item as the key and its index in the initial RDD as the value. This is actually a really handy trick to do early on in processing if you need to keep track of the positions of something, and then you're going to shuffle it all over the place, but you might want to put the order back later, because it lets you, at any particular time you choose, you can grab the indices, the ordering indices for the data. So and then once we've got this, we're going to do a collect, so we're going to bring this back, and we're going to print out the items in the partitions, the count of them, right? So what we've got are 2 things, and we've got 4,739 lines ended up in this item, and 4,467 lines ended up in that item. Right, and you can actually verify if you go in here, if you do something like a glom, if we go, say, glom.count, right, we can see there's just 2 items. Right? So these are not 2 partitions anymore. Once we've glommed, we've gone from 2 partitions to just 2 items. So this doesn't necessarily make practical sense for this particular task for the data, but what we're doing here is just looking at how the data is laid out in the partitions. So let's go and make a slightly more complicated DAG, right? So if we come back, these things are not very interesting, right? They're just tiny, right? We don't have a lot of operations. Let's make something a little more complex. So we'll take the lines here and we'll do a flat map. So what does flat map do? Right? So it does a map and then it unwraps the resulting collections. Right? So if we were to take each of the lines in the original RDD and do a map using this function, we would get a Python list of words. So if we did a map, we'd have a RDD of lists of words. But if we want just an RDD of words, we can use flat map, which will unwrap each of the lists into its elements. And then we'll pull those back. So let's do that. And this gives us, a RDD of words, but we mainly want to come over here and see what does that DAG look like. And as we add more operations, how does this break down? So here we've got our last operation here. Okay, well, it's still not too exciting, right? We've got a map partitions RDD. So this represents the flat mapping we did, but it's still relatively simple DAG. So what if we do a flat map and then a map? Right, so here we had 2 tasks, one for each partition. So here, if we're doing a flat map and then a map, how many tasks do we expect to see? If we have 2 partitions, we do a flat map and then a map. Right, so if all of these operations spawn tasks, we might expect something like 4. But remember about pipelining. Right? So map and flat map are both narrow transformations, which means we hope Spark will take the mapping on a partition and the flat mapping on a partition, and it'll actually do those together as a single task. So we would, given that optimization, what we hope to see here is just, again, 2 tasks, even though we're doing more than 2 operations on different partitions. So if we drill down in here, right, 1 stage, 2 tasks. Right, and it turns out it's still combined into a single operation there. Okay, so now we'll throw another little monkey wrench in. So each of these lines is just adding an operation, right? So we're reading the file, we've got the flat map into an RDD of words, and now we're going to do our hello world word count operation that you might have seen somewhere else when you first took a look at Spark, where we map each of the words to a pair of the word and the number 1, and then we would do a reduce by key. So for each of the words, we add up all the 1s, wherever they happen to be, and we come up with a total. And the result is an RDD of word and word count pairs. And why are we doing this? Well, reduce by key is a wide transformation. So that is going to trigger a shuffle. So we should see another stage show up. So let's see if that actually happened. Here's our word count. And let's go take a look at what that job looks like in the UI. So notice this. We had 1 stage, 1 stage, 1 stage, and now this latest job, 2 stages. Right? So as soon as we introduce that wide transformation, Spark picks up on the fact that there's a shuffle, divides into 2 stages. So there's 2 stages, and we can drill down and see what this, now this DAG looks a tiny bit more interesting. Right? Here's our input data. And we're going to do a shuffle, and we're going to pick it up in the output stage here, right? So we've got 2 stages now, the stage that's upstream from the shuffle and the stage that's downstream from the shuffle. So putting a shuffle in there has produced a job with 2 stages. And here we can see data on each of the 2 stages, right? Within each stage, we expect the operations to be pipelined. So if we have 2 partitions, we expect to see 2 tasks in the first stage and 2 tasks in the second stage, and that's what we've got, right? 2 tasks in stage 237, and then 2 tasks in stage 238. And notice here we can also see now that we can see where the shuffle data is going, right? So we saw we had the input of 412K, and now we're seeing 273K of shuffle right? So upstream of the reduce, or upstream of the shuffle, we're writing out 273K. And on the downstream stage, we're reading that 273K into the partitions on the other side. So I realize we're hitting our time limit for our afternoon coffee break. So I'm going to stop here, and let's see, how far are we on this notebook? We're actually most of the way through, but we'll pick this up after the break. So we'll stop here. We'll come back at about 2:45, and we'll look at a couple more operations here, and hopefully this will all make sense. And then after that, we're going to talk about Spark streaming. Okay, so let's pick up with a little bit more. We're going to take a look at caching and how we can see the size of our data, right? If we want to be able to cache big data and operate it in memory, it's useful to be able to see how big it is, so that if it doesn't all fit, we have an idea of what we would need to do to accommodate it and how much is being spilled and so on. So let's take a look at that, and we'll look at a little more about partitioning. And then we'll move on and talk about streaming. So before the break, we had done this, which was kind of our most complex of our simple DAGs that we're doing here. And let's see, let me make sure I've got my window up that has the UI. That's this one over here. So we had our slightly complex DAG over here. So we're going to come back to partitioning in a minute or so, but let's take a look at some caching, right? So let's say I take this text file and I call .cache on it. So let's go and see what happens. So if I go like this, if I come over to here, I would look for the data over here under storage. So this is where I would expect to see information about cached RDDs. And I don't see it in here. You see all of this tungsten project stuff. And this is actually stuff from when we were messing with data frames and caching that. But this is actually nothing to do with what we're doing now. So why does this not show up? Well, exactly, we haven't run an action yet. So when we say cache, right, that action doesn't happen, or I shouldn't call it an action, that operation doesn't happen right away. So cache just sets a marker that says cache this data the next time it's materialized. So if we do something to materialize this, then we can go and find the cache data. So we've got this marker on here. If we take an RDD and we call set name on it, that'll make it easier to find things in the UI. So this doesn't do anything in terms of our data, but it's helpful for humans. So we're going to call set name my cached book, and then I'm going to run count on this just to force it to run through Spark. And now I'm going to come back over to here and click storage. And let's see if I can find it. There it is. It's at the bottom. So here it is, my cached book. And it says memory serialized 1x replicated. So we'll talk about that in a second. That's the storage level. Then we have cached partitions 2. And this is probably all of it. It's not very big. Fraction cached is 100%, right? So we cached all of it. And that's the size, right? So this is size in memory. I'm sorry I'm scrolling around so much. I know that's annoying to look at on the projector, but this ended up at the bottom of the grid here. So we can see size in memory, external block store. This would be something like tachyon, or size on disk. So memory serialized 1x replicated. So what's that about? So when we persist RDDs, if we call cache, there's a default persistence level. So if we're working in the Scala or Java world, when we call cache, that's going to persist it in memory deserialized. So as basically Java objects. But when we're creating Python objects and running those through Spark, Python objects are always serialized using the pickle serialization. So the default serialization level when we do cache for Python objects is memory serialized, right? It's in memory, but it's serialized because there is no Java deserialized version of this, really. 1x replicated. So the default is to only have one copy of it in memory, but if we want, there are persistence levels we can specify that ask for this to be replicated twice. Why would we want to do this? Since we know we can always reconstruct part of the RDD, it's not that we're going to lose data. We may have a situation where the cache improves performance sufficiently much that we would like to have two copies of it. So Spark evicts things from the cache based on an LRU, like least recently used approach. So it could be that we need to replace the storage in one of the executors and we lose one cached copy. If we had it replicated, then there'd be a higher chance that maybe the other copy is actually still around in memory. So there's a bunch of replication levels, and we're not going to cover all those in the class here today, but you can take a look online. There's lots of great material. And basically, we can choose between memory, disk, memory and disk, doubly replicated, singly replicated. So there's a set of levels we can specify. But the reason it says serialized 1x here is because when we say cache, that's a shortcut for the default persistence level. So for Python, it's memory serialized. All right, so that gets us a view into our storage requirements for the cached data here. So what if we come here and go unpersist? Okay, so we come over here and we'll do a refresh and click storage. And notice that it's gone, right? So I know there's a little bit of a mess here from the data frames, but if you kind of take a look at the rows, you'll see that that thing's just gone, right? So what's the purpose of that demo? The unpersist is not lazy. When you do unpersist, it's gone. It's gone right away, right? So you gain that memory space back potentially, and you lose access to the cached version as soon as you call it. It doesn't wait for anything. So here's how we could specify a storage level. So here it says memory only serialized. And this is actually, because we're in Python, this is the same thing. Persist, memory only serialized, is the same as cache in Python. So in the Java world, cache maps to persist memory only, but not serialized. So if we go ahead and run this function here, let's see, I hope I did run that. And then we run count and materialize that, we should see the same thing pop up in here that we saw earlier. There it is, my serialized cache book, memory serialized 1x replicated. So we already did this particular DAG, so I'm going to skip over. Well, we can run it, but I'm going to skip over it for now. Let's take a look at this one here. So repartition to 4 partitions. So we're going to read it into an RDD with 2 partitions, and then we're going to repartition to 4. So is this a wide or a narrow transformation? Well, it has to be wide, right? Well, I guess it doesn't necessarily have to be wide because we could have 4 partitions, 2 of which are empty. Right? So theoretically, we could just ignore those, but that's not going to be an elegant use of our resources. And when we do this repartition, what we'd like to do is to get our data repartitioned either by hash or by range into the 4 partitions. So let's run that, and we'll see what's here. So when we talk about partitioning a data set, we didn't really talk about how does that partitioning work. So there's a couple approaches to this. One is if you've got your own data and you want to control the partitioning, you can manually partition. So you can pass a partitioner function that will allocate which items go where. So let's say you've got a very bizarre data set that does not distribute in sort of a traditional way, and you're finding that the built-in partitioning is giving you heavy skew, meaning there's some partitions that are always getting too much of the data. So you can manually specify a partitioner. But if you don't do that, the built-in partitioners either go by hash, so it depends on the operation, where we basically hash across a number of targets, or for certain things it makes sense to do a range partitioning. So we might partition by range. Like if we're sorting stuff, it makes more sense to partition by range than by hash. So the sort partitioner and hash partitioner are the built-in partitioners that we get by default. And then when we have an input source, the input source decides its own partitioning. So like the HDFS system of 1 block per partition. Or if you choose to repartition manually, you can tell it exactly how to partition. So those are sort of how the partitioning rules break down. But that's a great question, because it's good to have an idea, again, to sort of dispel the magic about what's going on here, is that there's a modest number of known algorithms that are controlling how this works, and we can look at the output of those and see if it's suitable, and if it's not, we know exactly how to override that. So that's a great question. So, okay, so we've got our 4 partitions here. We don't have anything in the UI yet because we haven't run an operation. So let's go and do this, which will count the items in each partition, and it'll also do an operation because it does a collect. So here we can see the 4 partitions, and we can see that this repartition does, it does what we would expect, which is it actually repartitions across the 4. It doesn't just create empty partitions, which would be really silly. And we've got 4 there. We would expect to see the exact same thing here. And you can see over here. But this is interesting. So notice there's a little bit of a difference here. It says 4 tasks out of 4, and then it says 2 skipped. Let's go and see what that's all about. So if we look at the graph here, we can see that over here on the left we've got a stage, but it says skipped and it's grayed out. So what's that about? Well, so when we involve a shuffle in our DAG, the output from the upstream side of the shuffle gets written to disk. And those files stick around on the disk, and Spark will keep track of them. So if we do another job that needs the same shuffle output, it'll read from the shuffle output files instead of recomputing the upstream part of the DAG. So what's going on here is we did a similar task to what we did earlier, but we didn't have to do all the computation because Spark said, wait, I know what's in those partitions, and I know they've already been calculated and that those shuffle files have been written to disk, so I'm just going to pick up the downstream side and go from there. So when you see grayed out chunks of the DAG or stuff that says tasks are skipped, that's what that means. So, and we have 4 for our downstream here, and then we've got our skipped stages. These are the 2 upstream tasks, right? Because we had 2 partitions on the upstream side. So let's do one more demo with this, which is handy. What have I cached here? I'd like to cache something and take a look at what that looks like. Let's go back to here. Let's do the cache. Let's leave it in memory. Okay. And now let's make sure that's running over here. Okay, there's our dot count. And now let's go and run this job again. Okay, so we come back here. We expect to see another entry, right? So there's another one. And if we click on here, this is the thing I wanted to show you. So see the green dot? So this is another feature or notation that you get in the DAG, right? So there's the gray sections for the stages that are skipped because we have shuffle output files, and the green dots represent cached RDDs. So this isn't changing the functionality. It's no different from what we did before. I just wanted to show you the UI end of this, that when you're reading from an RDD that's cached, it will be highlighted this way so that hopefully you're getting the feeling that from these UI tools, they're not just pretty pictures, but you're getting an idea of how you can figure out how your job is running, what's fitting into memory, what's actually being cached, whether you're able to skip the stages you'd like to be able to skip when you're doing multiple operations. Okay, I just wanted to show that really quickly, and then we'll come down here. So we can add some more. Partitions. So if I come down, yeah, I guess I'll do each of these. We'll take a look. So here we've got 2 when we're reading. We're repartitioning to 12. We're then caching that, and then when we do a collect, we're going to pull that stuff through. So let's go take a look. So now we've got a slightly more complicated DAG, and you can see here the number of partitions, right? So there's 2, then there's 12, and then there's 12 in the subsequent stage, right? So we've got a stage boundary here, right? Because repartition triggers a shuffle, and we're going to have another stage. Then we have a reduce by key, so that creates another stage, right? So that's why we saw 3, right? There's 1, then there's a shuffle, then there's another one, then there's a shuffle, then there's the downstream part. So there's 3 stages. And why do the downstream ones here have 12 partitions? Well, I wasn't going to go too far into this, but I don't want to be evasive about it. So the parallelism here is controlled by this property. This is scrolled. Spark default parallelism. So spark default parallelism, that's what's going to control how many partitions we've got on these calls where we don't specify it. Right? So in this case, it's the largest number of operations in a parent RDD. So here we had just one parent, it had 12 partitions, and so the spark default parallelism is going to say we're going to have 12 partitions in the child. So that's why we've got 2, then 12, then 12 here. Here, if we go from 2 to 4, and then we do a reduce by key, we expect to have 4 at the end also. So let's take a look. And that's what we get, right? 2 when we read, then 4, and then that number of partitions 4 is retained in the second, after the second shuffle. You can also see the read and write quantities that are going for each of these, right? So in the first stage, at the end of that, we wrote 333K out, and in the next stage, we read that 333 in and wrote out 308K of shuffle data, and the last one we read 308 and we didn't write any. And the very last one, we turn a couple more dials here, so we have 2 when we read, we repartition to 12, and then we cache. Then we have flat map and map. These are all pipelined. They're all part of a single stage. Then we do a reduce by key to 8 partitions. So when we do these wide transformations, we can add a second parameter that tells how many partitions we want on the downstream side of the shuffle. So I don't think we've seen that parameter yet today. It's optional, right? So we saw how the default parallelism works if we don't provide that. But if you want to specify the number of output partitions from a shuffle, you can do that like this. And if we do a collect, we'll run a job there. If we do get num partitions on the output, we've got the 8 that we specified, and we can come over here, and we should be able to see that. So 2, and then 12, and then 8, and that's why it says 22 tasks were executed, right? So it's always 1 task per partition. Okay, well that's pretty much the end of this here. Like I said, we weren't going to derive any awesome data insights into Tom Sawyer. What we really wanted to do was poke and prod Spark with different configurations going in so that we can see how the DAG is executed, and we can see things like whether the data is cached, the quantity of data that's being read and written in shuffles, the number of partitions, and we can see how we can control that so that we can tune our jobs. So at this point, we've talked, to the limit that we can do within the time we have here. We've talked about APIs. So we talked about the basics of programming with RDDs. We've talked about the basics of programming with data frames. We've talked a little bit about the internals, a tiny bit about data frame execution optimization, and now we've talked about the general Spark job execution. So that kind of covers the basics of core Spark, and so we've got a little bit of time left this afternoon. What we want to do is talk a bit about streaming and a bit about machine learning. So for streaming, we're going to talk about how it works, and we'll do a little application. For machine learning, we're not going to talk as much about how it works inside because there isn't really special internals for machine learning. Machine learning is really algorithms are implemented. So we'll talk about how we prepare data for machine learning, and we'll run some stuff on there to see some patterns about using it. So we'll start with the streaming, and we'll spin this up here. So the idea is that we'd like to be able to take data from various streaming sources. So it could be watching a socket, reading from Kafka, reading from Flume, HDFS. Well, those are static files. How is that streaming? Well, we can do things like watch a folder, and we can treat new files that appear in a folder as part of a stream, right? So if you have a log rotator, for example, you may have code somewhere that rotates log files, right? So they get moved from one folder to another. Well, we can treat that sequence as a stream. We can even treat a sequence of RDDs as a stream. We can also read from things like Kinesis, right? So Amazon's got its own streaming system, or from Twitter, which you see, I'm not sure how frequently that's done in production, but it makes for nice demos to read from the Twitter stream. And then we'd like to be able to do things with that data, and then we're going to send it somewhere. Right, so the data keeps coming. We can't really just hold it all in memory, but we can do some operations on that, and then we can send it out to things like HDFS or S3 if we want to archive it in a data warehouse. We can put it in Cassandra. We can put it out in dashboards for customers or executives to see, or whatever we might want to do with it. And we can also combine our streaming data with other algorithms. We can combine it with static data or ML models. So that's the idea. And that motivates the compromise that we have for Spark streaming. Right? So Spark streaming is sort of in the intersection, or it's either in the intersection or perhaps in the neither category of what we've got here. Well, I don't know if this Venn diagram is quite accurate. It's probably the best way to say it. It's nice, but what we've got is, on the MapReduce side, we've got a great system for doing batch processing. With things like Storm and other real-time streaming, we have isolated pieces of data that can be processed one at a time. And what Spark does is maybe conceptually it belongs in the center of the Venn diagram, because what it does is it conceptually processes streaming data by treating it as a sequence of batches. Right? So it's sort of a both and neither. It turns out that that's actually really handy, because although it doesn't maybe have the individual event processing speed of something like Storm, right? You're not going to process things with Spark streaming in like 7 millisecond latency. That's not something that's currently a possibility. On the other hand, you can do it reasonably quickly, and you can use the same APIs that we've been dealing with to interact with this data and to combine it with other batch stored data or machine learning models or whatever you might like. So just some examples of how this might be used. You can pull it together. Web analytics is a common use case. You grab all of this data about what people are doing on your website, you put it in some kind of a message-oriented middleware or a queue like Kafka, and then we can pull it out into Spark streaming and do things with it. So we could report on it, or run it against an ML model or something like that. We might take data from, say, smart meters and data from weather. Maybe one is coming via Kafka and one is coming via Flume, and we could join these two things together to try and draw conclusions. Like, are we going to need more power in a certain area of the power grid? Or maybe we can predict when we're going to need to send service crews to certain areas, because we can predict physical disruptions to the grid, something like that. So that's just sort of a general overview of where Spark streaming fits into the world. So how does it actually work? How do we do this thing where we are able to treat streaming data kind of like batch data and use the same API? So what we do is we use this model called micro-batching. So we set an amount of time, which we call the batch interval, and we say that we're going to pull data in, and every so often, where so often is defined as that batch interval, we're going to make an RDD out of the data that's come in. And once we've got an RDD, we can do all the usual RDD things, right? We can do RDD coding, we can do data frame coding, we can send it to other destinations. So the Spark streaming pattern is to take an input of streams of data, to sort of discretize it, break it up into batches according to a set interval. And the set interval, like I said, it's not in the range of milliseconds. It's probably in the range of, say, half a second up to multiple seconds. And then we're going to, once we've ingested that, we're going to run it against certain jobs using Spark Core, and we'll see where that goes. So the way this works is that we have a batch interval that we set when we set up the stream. And I'll show you the APIs, but I want to communicate kind of the concept here. We call these things D-streams, or discretized streams, because they're made up of sequential chunks of data. So we set this block interval, maybe 5 seconds here. And actually, this is maybe, well, it's maybe not the easiest model because of how the 5 is not easily divisible by things. But if we ignore the fact that 5 is a prime number here, so this is going to be an RDD, but it's not an RDD yet. When we start out, what we're planning to do is to create an RDD out of 5 seconds worth of data. And within that, we're going to have smaller collections of data. And the smaller time intervals, so this is all on a timeline, the smaller time intervals are called block intervals. So we've got a batch interval. Now you see why I've got the issue with 5. Maybe if we had a 5-second batch interval and a 100 millisecond block interval, right, then it divides really nicely because we get like 50 blocks in one batch. And each block that gets ingested is going to become a partition of the RDD for that batch. Okay, so I know there's a bunch of words flying around here, but I'll say it again kind of slowly and try and be as clear as I can. So if we set a batch interval of 5 seconds, it means we're going to get an RDD every 5 seconds. Within that 5 seconds, if we set a block interval of 100 milliseconds, it means that every 100 milliseconds, the data that's been gathered will become a partition of the future. It will be a block that will become a partition of the future RDD. And at the end of 5 seconds, we would expect to have 50 blocks like this. So we would expect to get a RDD with 50 partitions. And then we just start over again, right? So we've got one RDD, and then we do the whole thing over again, we get another RDD. Right? And that just keeps running, right? So that runs, that should hopefully just be running indefinitely. Now that means we need to do something with the data, and we need to do something with the data fast enough that it doesn't back up, right? So we've got to take this data and do something with it and then hopefully send it off somewhere. Now once we have one of these D streams, so D stream is like an abstraction that represents this whole streaming behavior. Once we've got a handle to this D stream, we can actually do operations on the entire D stream. So there are shortcut operations that allow us to operate on the stream, and basically what it means is operate on all the RDDs that flow through that stream. So if we go back to our log lines example, we might have a stream of lines of data, and we want to do something like a filter operation on all of those lines. So in the RDD world, we said, well, for the RDD, we want to do a filter. Here, we want to say that we'd like to filter every RDD that comes through. And for many of those common operations, like filter, we can actually do that on the D stream itself, right? So we could say, well, I'm going to take these, so initially we've got these blocks, they become a D stream here, and we can then say I'd like to run a filter, or in this example flat map if we're doing word count or something. I'd like to run this operation on the stream, which means run it on every RDD that comes through the stream. So the idea is that we can treat the streams almost like RDDs. And if the stream API doesn't have the behavior we want, we can always drop down to the level of RDDs. So there's an API called transform that lets us manually specify a transformation on every RDD. And there's also a action called for each RDD that lets us specify an action, like save to Cassandra would be an example, right? That's not a transformation. It's like every RDD that comes through, we want to write it to Cassandra. So we could say for each RDD, and that lets us drop down and use any code that we have from anywhere that we've written or that we've received that works on RDDs. We can work on the streams. So this is the architectural model of Spark streaming: is we have a batch interval, and each batch becomes an RDD. Those RDDs have a partition for each block, where a block is defined as a smaller time interval inside the batch interval. And then we can call high-level operations like filter or map or flat map on the D stream itself, meaning do this to all of the RDDs that come through. And we have some escape hatches like transform or for each RDD, where we can always go in and program directly against the individual RDDs coming through if we want to. So that's the overall way that Spark streaming is built. So we're going to look at a little more with the ingestion, and we'll do some labs, but I'm going to stop here for a minute to see if we can do a quick survey on the class just before it gets too late this afternoon. So I'm just going to stop here for maybe 5 minutes, and if you can go to this URL, it's a really quick survey. It's at the bottom. It looks like you have to do more pages. It's just one page. And so we can collect some data about what's really good or what's not as good about the class, and then we're gonna keep going with this, and we'll do a streaming lab. Okay, so if you're still working on the survey, that's fine. There's no worries about that. But I'm gonna pick up here with a little bit more about streaming, and we'll get some code running. So here's a complete example of a streaming program. It's similar to or kind of based on the one that you'll see in the Spark Docs streaming guide. And we can take a look at how this works. Right, so this is actually a complete script. You could run this whole thing as a program. And what we're doing is we're importing the streaming context object. So this is set up, the Spark context is set up that, again, you don't need to do in the notebook or the shell. Streaming context you do, right? So streaming context you need to create yourself when you want to use streaming. And you give it a Spark context, and this number 1 here is a batch interval. So what we're saying here is we want to use a 1-second batch interval. Right, so underneath we're going to have an RDD every second. And then we're going to configure what we want to do with this stream. So before we start the stream, we have to wire up all the things that we're going to do with it. And you can use the same streaming source to do many different calculations, all within the same streaming application. So it doesn't have to be linear. It can be kind of complex, but you do have to wire these operations up before you start the stream, because once you've started it, you can't alter what's happening. All you can do really at that point is run it or stop it. So we're going to say, let's create from the context a dstream using this socket text stream helper. Right, so there's various different APIs for creating streams from different sources. In this case, socket text stream is going to connect to this socket, and it's going to just read in lines of text when they become available on this socket. So in order to get this to do anything, you would need to have something providing data there or run netcat on it. Like in the next slide, we'll look at how you could do that. But here we're more interested in the Spark end of things. So on the downstream side where we receive this data, this is going to give us something called a lines stream, or we're calling it lines stream. And that's a dstream that we can then put more operations on. So we could say take the stream of lines and then let's filter it by finding the lines that have the word error. So notice this looks a lot like the RDD code. Right? But really it's a little bit different. It's a little bit higher level, because this is saying, really it's saying for every RDD that comes through the stream, run this filter on the data, and the RDDs that would be the result of that will make up something called error line stream, which is another dstream, right? So we can take a dstream, do a dstream transformation, and get another dstream, and we can add as many of those on as we want. This pprint is an action on the dstream that it's mainly for debugging. It takes the first 10 items from each batch and just prints them to standard out. So it's really handy for testing. It's more or less useless for real applications, but you can use this to make sure your integration is working. So if we run this, we would expect to see a timestamp and the first up to 10 items that are coming through in each batch. Then once we've got all this logic wired up, we can say ssc.start. So this will actually start the machinery running. And if we're running outside of the notebook or some other long-running process, we might want to say await termination, because we want to keep this thing running. So if we run this, and I have a notebook that I'll show you, you can kind of try this. We're not going to really do it as a lab, but you're welcome to run it yourself and see how this works. That's pretty similar to this. If we were to go into our terminal and say run netcat, actually we're missing a couple of command line flags here. If you want to be feeding things in through netcat, I think you need like a -L and K so that it's listening and it doesn't shut down. But the idea is that if we're feeding data in here and over here we run our code that's listening on that same port, we would get these lines coming through and we would only see the ones that passed our filter, right? So if these were the lines that we typed in or piped or something over here, then over here we would get a timestamp, and in the first batch maybe just this line with error. And in the next batch, so here's a second later, we get maybe these lines, but we only keep the one that says error 4 happened. So we can visualize how this is working across a cluster. In this picture, this icon up at the top represents the streaming source. So in this case, it's localhost port 7777. It could just as easily be Kafka or Twitter or something else. And this larger rectangle represents the batch interval, and the smaller blocks within this represent the block interval. Right? So we can kind of look at this in slow motion and see how the data is ingested. So out here on a worker, we have a number of task slots. These circles represent maybe cores or maybe threads, but they're basically slots for executing tasks. And the highlighted one here with the R in it, the orange one, that stands for receiver. So in a normal or traditional Spark streaming configuration, you have to dedicate a thread to doing the receiving, right? So we're actually using up a task slot here, or we're using up a thread as a receiver thread. So this guy here is the one who's doing the listening. Now there are some ways to ingest data into Spark streaming that actually don't require allocating a thread and have some other interesting benefits. We're not going to have time to talk about that in here, but before you go home and deploy Spark streaming, look at the Spark Kafka integration guide, because there is a different way to ingest data using a receiver, or not actually a receiver, using a interface called Kafka Direct. And that it behaves a bit differently from this and has a number of really, really nice features for if you're deploying something in production. So we can't talk about that right here. I could talk about it after class if you want, but definitely look at that before deciding how you're going to go to production with this. But in this model, so if we're using a socket text stream, we have to dedicate a thread as a receiver. That's this guy here. So in the first block, so in this colored in period here, about say a third of this, or 200 milliseconds, we receive some data, and we're going to do a couple things with it. So we're going to take it here, and we're going to write it. We're going to write it at least to memory over here. And we're also going to replicate this to somewhere else in the cluster. Right? So with streaming data, we may not be able to easily recreate this data. It depends on the source. But with certain kinds of sources, like a socket text stream, we can't go back and ask for this again. So one of the things we're going to do is we're going to replicate this data when we ingest it. So it's going to go to two places in the cluster. So we put a copy here, and then we'll put a copy maybe over here. And in the next block interval, we get another chunk of data, and we'll put it over here, and we'll randomly pick another executor and maybe put it over here as well. So we've got two copies of that. And then another block interval goes by, and we take that data and we write this also to two different locations. And now we've reached the end of the batch interval. So at the end of the batch interval, these blocks of data get promoted to become partitions of an RDD. Right? So now what we have is an RDD that has 3 partitions. There's 6 purple triangles because there's 2 copies of those partitions somewhere in the cluster. But there's really just 3 partitions in the RDD because there's 3 blocks in this batch interval right over here. Right? And then we can go on from there, and we can start ingesting more data in the next batch. There's a visualization UI. So when you're running a streaming job, a tab will appear in the Spark UI that says streaming. It's right there next to jobs and executors and storage, but it won't show up when you're not running a streaming job. And when you're running a streaming job, you can click in there, and you can actually see graphs that show the rate of ingestion in your different receivers and the sizes and how long it's taking to process them. And when each batch gets processed, you can drill down on that job and see all of the normal Spark details for that particular batch. So there's a nice UI for that. Maybe we'll take a look at that when we do the lab. You can receive input from 2 streams and do things with them. So you could have 2 streams that are maybe reading from the same source, or 2 streams from 2 different sources. And in this example, right, we've actually got 2 receivers. So we've got a receiver for each of these, and we're just writing out 2 collections of blocks that become 2 RDDs in parallel. So here are our blocks, and then when we move on to the next interval, those become RDDs, and we could union those 2 things together. Right? So that's how some of the streaming receivers handle multi-threading, is you can have multiple receivers that receive in parallel, and at the end of the batch interval, you union those RDDs together, and now you've got one RDD that represents all of the blocks across both of those receivers during that interval. So in the older Kafka model, so I mentioned this Kafka Direct. Prior to Kafka Direct, or in the sort of older Kafka receiving model, we used a receiver for each Kafka topic. And so if we wanted to create more than, if we wanted to have parallelism there, we needed to have more than one Kafka receiver. So you could do something like this. You could actually say, I'm going to have 5 of these Kafka streams. I'm going to create, this is Scala code here. I'm going to create 5 different Kafka streams, and I'm going to union all of them. You can also do joins on D streams. Right? Now, for the join to make sense, you need some kind of a key, or something to join on, but you can have streams that you actually join when they come through as well. So we're not going to look in depth at all of the streaming API. There's just too much to do here, and it's not the most useful thing for the time limit. But what we've got is sort of a little bit of an overview of the things you can do. So we have things like map and flat map and filter. We can do reduce. We can do union. You can also do things like reduce by key, or update state by key, which allows you to keep a long-running piece of state that's updated as stuff comes through. Right? So there are certain kinds of problems like sessionization or other things that are over a longer period of time where there's no reasonable way to get an answer from a single RDD. That's not helpful. So there are a number of features that allow us to span longer periods of time. So things like update state by key, where we have state that's updated continuously every time a batch comes through. We'll also see an example in one of the notebooks of windowing. So you can take a stream and you can say, well, I'd like to derive a stream from this that represents a wider window of time. So we could smooth results maybe by including some lead and lag across the data. So we're not going to have time to go into that, but I definitely want us to have a chance to take a look at the lab here. So what we're going to do is we're going to start with this anonymous edits lab. And this is really cool because we've got a live server that's going to feed us the anonymous, well, actually, they're not all anonymous, all of the edits actually to the English Wikipedia in real time. And we can bring them in and measure things about them. So I'm going to clone this. And I'm going to put this in my home directory. So something like this. And I'll switch over to there. And before I even run this, I want to show you this server, right? So this is, I was testing this earlier. If I turn this on, so all I'm doing is I'm pointing this at a particular IP address. So this comes from some node code, which comes from, I think, an IRC channel, but there's some infrastructure out there that's receiving the feed of all of the updates to Wikipedia, and we can actually watch this stuff come through. So these are all the changes. These are English only, so this is not every Wikipedia site, but it's the English Wikipedia. So these are all of the edits that are coming through to various different pages in real time, and what we can do is collect some of those using streaming, using Spark streaming, and then we can analyze them. We could say things like, how many people are logged in versus doing anonymous editing, and where are the people who are anonymously editing coming from? Are we seeing a lot of anonymous edits coming from a small range of IP addresses, suspicious things like that? So there's lots of fun stuff we can do. So we'll actually do that. I'm going to kill this in the shell, but we're going to pull this over here into Spark. So first I'm just going to do a bunch of imports of some things that we're going to want. So we're going to want some stuff from PySpark SQL types, PySpark SQL, PySpark streaming, and some helper stuff like the JSON parser. It may not have been totally obvious, but this is a JSON. These are JSON formatted records right now. So we'll use Python to decode those. So we'll do some of this. First I have to attach. So this is where it's most important that you attach to your own cluster. So one of the things that makes working with streaming a tiny bit challenging in the notebook environment is that we need to be careful about when we start and stop the streams, and we can only have one streaming context running at a time. So you definitely want to be on your own cluster for this. And we're also we'll generate some values here. This includes things like where we're going to write the files to that we bring in, and the port and IP address we're going to connect to. An error with the imports. Let me take a look. Yes. Okay, so I will attach this. Let me set this to attach to all clusters. So this is just some Databricks infrastructure where you can load up libraries or specify them on the shard here, and then we can configure whether and when they're attached to different clusters. So thanks for pointing that out. It looks like that's the only one we need because these other ones are Scala only. So let's go ahead and try that again and see if it works better now. Actually, let me go on to the second shard because there may be people on shard number 2 over here, and I want to make sure it's set up the same way over here. So we'll go. So I'm going to go create library. I'm going to go Python, and I think I can go IP address and go like that and go like that. And there we go. Okay, so at this point, so that wasn't, honestly, I didn't intend that to show it off, but that shows a little bit of the infrastructure on how you can bring in other chunks of code. So whether they're libraries from whether they're Scala, Java libraries, Python libraries, you can bring them in and manage them in the environment here. So let me know if any more problems occur with that. So we'll come down here and we'll set our batch interval to be 5, which in the Scala API means 5 seconds. And what we're doing here is making sure that we have a place to put our data when it comes through. So we're going to collect data for a brief period of time, maybe 30 seconds or a minute, and we're going to store it into some files. So this is one of those things that's a tiny bit awkward to demonstrate in a notebook, because in real life with streaming, it's a stream, right? We have data coming in, we do stuff to it, and it goes out somewhere. And if we want to monitor it, we typically monitor it on the downstream side. So we might have a report or a dashboard that comes from maybe a database that's receiving all of this data. Here we're trying to do the whole thing self-contained. So we're going to receive data for a bit, and then we're going to store it in some files, and then we'll analyze what shows up in those files. So now we're going to go down and take a look at some logics that has some helper functions for doing this. Right, so what we want to do is we want to receive things through our text stream. We're going to JSON parse them. This point actually doesn't apply. We're going to parse them, but we're not going to convert them to Scala objects. That wouldn't be any fun in here, so we'll just take that out. We're going to filter out some edits that don't apply to articles, right? So we don't want to, for example, care about edits to someone's profile page. And then we're going to save out the changes. So we have some helper functions here. So let's see. We'll start with the start function. So there is a helper on streaming context called getActive or create. And that will allow us to create a stream from this function, create context, or if we're recovering from a failure, we'll detect the files from the previous jobs over here in the checkpoint directory. So we can reconstitute on failure using this helper function. Hopefully we won't have any failures here, but that's what this API does. If we don't find any data from a previous failed run, we're going to run the create context function. Which uses the same API we just saw in the example slide. So we make a streaming context from our Spark context and using our batch interval of 5 seconds. Checkpoint tells Spark where to put the checkpoint data so that we could recover this if we need to. And then we've got some logic that operates on the stream. So we'll take on the context. So we'll start with the context and make a socket text stream. So this is just like the localhost 777 thing we just looked at. And we're going to call the result of that base DS or base dstream. And then we're going to say base dstream.map. Right? And what does that mean? It means for every RDD that comes through this stream, do the following to the data. Take the JSON data that comes through and convert it using JSON.loadString over here. Then we're going to define a helper filter called filter out special pages. This is a little bit like the filter we wrote earlier. So it takes an edit object, Sorry this keeps jumping around. I've got a little limited resolution on this display here. So we're going to take the data that comes through and we're going to look and see whether the URL matches this regex that was defined for the special pages. So we're basically doing a regex check and decide whether to keep the edit. And then we're going to call filter on the dstream. So we're going to say take the dstream and filter using filter out special pages. And at that point, we've got a dstream we're going to call articles dstream. So articles dstream represents it's been decoded by the map from JSON into a Python object, and then it's been filtered to throw out changes to pages we don't care about. So that's articles dstream. And now we want to see whether we've got an anonymous edit that has an IP address. Because if we have an anonymous edit with no IP address, and there are some of those, we can't do anything with it for this lab. So we're going to write another filter. So we're going to make this function called valid user, and it's basically going to look at some fields in this JSON object, and it's going to say if the user's logged in, we keep it. If we've got an IP address, we'll keep it. If we don't have either of those things, we're going to throw it away. And we're going to use that by going articles dstream.filter and pass valid user as the filter function. Then we're going to take that dstream and we're going to map it to an output function for making JSON, and then we're going to write that into text files into the folder that we've configured. So remember, we have to wire up all our streaming logic before we start the stream. So we're going to do all this stuff, then we're going to go ahead and do a ssc.start, and we'll return the streaming context, and this is all underneath this function here, right? So this gets called when we call getActive or create, and that gets called when we call start. So basically, when I run this, we're setting up code. Nothing's going to run yet till I go ahead and run start. So I'll come down here and we'll run this, and it says, OK, fine, you've defined a bunch of things. There's also a restart helper in there. So restart does a stop and then a start, so if something's running. Because if it's already running and you try to start another one, you'll get a nice error message there. So we've got a little helper for that. So now I'm going to go ahead and I'm going to run this. Well, hopefully it's streaming stuff. How can we tell? Well, there's a couple ways we can tell. One is we could look at the output directory and see if stuff is being written. OK, well, something's being written, but it doesn't look like there's much there yet. Let's write some more stuff. OK, now we're getting some files being written. But while the streaming is running, let's take a look at the Spark UI, because that's another way to see what's happening in here. So if I go to my same shard here, go under clusters, find my Spark UI. So this is the same Spark UI, but notice now over here on the right it says streaming. So this streaming tab shows up because we're currently running a streaming job. And if we click on that, we can see data about the currently running stream. So we've got a graph here for each of the receivers. We just have one receiver, so we've got one. If you expand this, you'll see there's just one. Socket receiver number 0. And it shows us our events per second over time. We get a histogram, so we can see kind of how much data we're ingesting. You know, is it smooth? Is it chunky? Scheduling delay and processing time. Right? So the assumption is, well, the data keeps coming. So our operations on this data had better happen in less time than the data that's coming in. So if our processing time is starting to approach our batch time, we're going to run into trouble. If it actually gets to that point, then we're definitely going to run into trouble. But we can see that our processing time is quite a lot lower than our batch time. Our batch time was 5 seconds. And our processing time here, you can see most of these are pretty quick. So we've got 2 batches up to 1.39, right? And half the batches are less than 0.83. So this is all not doing too much, and it's all running pretty quickly. And down here, you can see an entry for the jobs that are kicked off for each of the batches. So if I click on one of these, it will take me, well, once I have the data there, let's go back here again. Let's see if I can find some data here. Well, I'm not finding the data at the moment, so I'm not going to mess with that too much. But once we've got this stuff processed into the UI, you can get all of the normal job visualization for each of the batches. And over here, you can see things like how much data and how long is it taking. Let's try one more and just see if we've got anything here. Okay, hit refresh and it worked. Okay, so you may need to hit refresh. I don't know why it wasn't coming up right away. But here we can see a little bit of stuff that's running in this particular job. So we can see these various things running in here. So now we probably have a whole bunch of data stacked up. That's probably plenty. So now I'm going to go ahead and I'm going to stop this stuff. So I'm going to scroll down and go ahead and run stop. And if you come back over here, notice that the streaming tab is gone altogether, right? There is no streaming tab at all when you're not streaming. So that's just that button on the right's just gone. So now we're going to go and load up the data that we just ingested and see if we can figure out some things about it. So we've got this load edits helper. And what is this thing going to do? It's going to do a .text file and load up the files that we wrote. And it's going to map them from JSON back into objects. And then we're going to run them through this convert function. And the convert function is going to parse the timestamp. And then we're going to convert that to a data frame. So we're going to say, once we've got an RDD that's in the shape we want, let's go ahead and do a create data frame on that. So we can do data frame stuff. So once we have load edits defined, we can go ahead and do that. We'll get back a data frame, we can count it, and we can dump the schema. So let's do that and see what happens. Okay, so it looks like we've got 290 edits. And each edit is going to be a row with these columns in our data frame. We're not actually going to use too many of these, but this is what it looks like. We're interested in this anonymous field. We're interested in the user field, which is where we're going to find out who it is. So we actually just ran this. We don't really need to run that again. You can if you want. Well, I don't even need to run that line either. Okay, so there's our edits. So now here's something interesting, right? So remember how partitioning works for the streaming here. Like, we're not getting a lot of events in each batch, let alone in each block. So probably what we have here is a whole lot of partitions that have very little data in them. Right, so that may not be terrifically effective. Let's go and take a look at how the data is spread across our partitions. So what we're going to do is we're going to take our glom function. Remember what glom does. It takes an RDD and it makes an RDD of items where each item is the data from a partition in the parent RDD. Now we're going to do this map partitions with index trick again. And what map partitions with index does is it takes the partition, it gives us an iterator over that partition, and it gives us the actual number of the partition. Because remember, each partition in RDD does have an index. And then we're going to go and map this and add the length of the iterator. So how many things are in that partition or were in that partition. And then we'll pull that back. And then we're going to print a little report. So this is basically printing a report from there. So let's go take a look at what that looks like. So here's what we've got. We've got 422 partitions with 290 items in them, right? So we got lots of empty partitions, and we have partitions with very few things, right? So 1, 1, 0, 1, 1, right? So, right, this is not, this is a lot of partitions that are either empty or nearly empty. So let's go and reduce this to some smaller number of partitions. Right, so why does this happen? Well, we just talked about it, right? We have lots of block intervals that have nothing at all in them. And then we have whole batch intervals that only have a few things, right? So we don't have too much data coming through in this particular stream. So in a situation like this, it makes sense to maybe repartition down to a smaller number of partitions. So we could say something like, let's repartition into a situation where we've got at least 1,000 items per partition, or if we can't do that, let's just put it into 4 partitions. In this case, we only have, we're only going to have 4 partitions because we don't have nearly enough items to, trigger this first part. So we're going to call this output of repartitioning df2. Now we could say, well, how might we increase the number of records in each partition of the, these are actually not Parquet files, so I should change that there, text files. But this is a good question. Like, so what if we didn't want to repartition? What if we wanted to set this up so that we were naturally getting more items into partitions? What levers do we have that we can work with? Sorry? Exactly, yeah. We can crank that batch interval way up, right? So if we have relatively small stream, there are real applications running with 30-second batch intervals, right? So for some applications, 30 seconds may make sense. So let's go and take a look at how many anonymous edits we've got here, right? So the anonymous column gives us true and false, right? We can actually take a look at that. Let's look at this data frame. So I'm just going to insert this in here, and we'll do like a dot show on here. So we're grouping by, oh, sorry, this is the, so we're grouping by the values of the anonymous column. And you can see that what we're getting here are basically values of true and false, where we've got about 70 anonymous and 220 non-anonymous. And if we feed that exact data into display, we can make a pretty picture out of it. So this is the same data frame I just did, only I'm calling display on it instead of show, and so we get a nice pie chart. So we're also going to do an example. We can look at how we could integrate an external library. So there's a number of libraries we can bring directly in here, like matplotlib, right, is a really popular library, or ggplot2. We can also just bring in random JavaScript. So we're looking at an example of how to bring in Google Charts rendering from something like this. So let's go ahead and, we already did this. This is what we just did. Let's go ahead and bring these guys in here, and we'll convert them. Right, so we've got basically a native Python object that'll describe how many true and false, the same data we saw before. And now we can bring in our HTML. So this is not really Spark. This is really more of a demo of how we can integrate HTML into the notebook environment here. So we'll use a little string templating help from Python. And we'll use a template for some JavaScript here that uses Google Charts. And we're going to evaluate that, and then we're going to substitute in values from our Python dictionary we just cooked up. So same exact data we just saw. And now we can run this in the notebook by calling display HTML. Right, so this lets us run arbitrary HTML inside the notebook. So it gives us even more visualization options. So now we'll let you try a couple of exercises here. Right here at the end. So one of these is, what if we wanted to look at anonymous versus authenticated versus robot edits? Right, so here we've looked at anonymous, true or false, but there's also a robot field that'll tell you if it's a robot edit. And there's a couple ways to do that, because here we're trying to derive a single value based on the presence or absence of a value in more than one column. Right, so one way to do this is to use a SQL case statement, right? Load this up into Spark SQL. Another way to do it is to use the when and otherwise column function. So in Spark 1.5, there's a bunch of new data frame column functions, and two of these are when and otherwise that let us basically inline create if-else type expressions that produce column values in a frame. So this one's a little bit tricky, but you can try that if you want using the SQL or the data frame version, and there are solutions for both of those in the solution notebook, I think. If not, I'll make sure I get you both of those. So you can try that. And what we can also do is look at the anonymous editors, and we can look at the spread of those across different IP addresses. So we can do something like this, where we say, let's go ahead and pull up a data frame called anon.df. So this is pulling out just the anonymous edits, and now what we can do is we can try and pull out the IP addresses and the number of edits associated with that. So we can see, do we have IP addresses that have a whole bunch of anonymous edits associated? Because that's, that's a pretty big rules-based clue that there's some shenanigans going on. So we'll take a few minutes. You can try that out, and then we'll look at a solution for this. Okay, let's take a look. We'll take a look at this here. So I mentioned there's two different ways to do this first part. So the SQL case statement, this is basically just dropping down to old school SQL, which gives us a nice way to do it. I don't know if I want to call that cheating or not. Remember, because of the way Catalyst processes this stuff, if we go out to SQL, we don't really pay any price for that. So there's absolutely no loss. Well, I shouldn't say absolutely. There's very, very microscopic loss switching languages when we're doing something with data frames. So you shouldn't need to worry about that. But if we wanted to do that, we could register as a temp table and then basically run an old school select case and then do a group by this new column. If we want to do it using this new Spark 1.5 if-else structure, that's a little more interesting just because it's new and it looks like this. We would say, okay, we want to do the select. That's analogous to the select in the SQL case. So we want to project out. But what we want to pull out of here is a derived column. So if we import our functions as something like f, we could say something like f.when, and then we're going to provide a predicate here and a value. And then we're going to say, and from that column, we can compose that and say, well, .when the anonymous field is equal to true. We'll use the anon value. And then for the else part, we can use this otherwise. So we're basically saying otherwise, that will be the value. Now that's going to give us, if you were to stop there and do a show, you'll get a really, really wild column name from all that. So it's going to be impossible to talk about that column when we want to do the group by. So I'm going to immediately alias it as something friendly and then group it by that alias. So I'll call it status. I will group by status, and now I can do like a count and a show. So this will give us counts for each of the distinct status values that we got from that three-way if-else. So we'll get out a little data frame here, robot, authenticated, and anon. And this is a neat example because it shows how we can derive a value in a synthetic column from values that live in other columns, right? Because we referenced both robot and anonymous, which are two totally separate columns to derive this one here. So it's not that this is a totally new idea. I mean, you do it in Microsoft Excel, right, for the last 20 years. But it's nice to have it right in here. So we can run that either way, and then once we've got this grouped by type data frame, we can run it into display, and we can generate some kind of nice chart if I can actually get this to render. That's pretty weird. Let's try this again. Well, it doesn't really matter because they're both named grouped by type, right? So as long as I have one of those, it shouldn't really make a difference. But hey, we'll try it. Right on. Thank you, sir. That's fantastic. I love when you guys can help me do it. Cool. So we get a pie chart here. I'm not sure why we weren't getting that from this one above, but I'm not going to worry about it right now. So we can look at which kinds of edits we're getting. And we're lucky here. A lot of times you don't get any robot edits when you try this out because they're not as frequent. So I'm glad we got a few here. A lot of times you just get two colors in this chart. So what about the anonymous edits? This one's a little easier. Because what we really want to do here is we're going to pull out these, I think we already did this, we're going to pull out the anonymous edits, And what we really want to do is group by user, because in the case of an anonymous edit, this user is going to have the IP address in it. So we're going to pull this user out, do a group by on there, and then produce counts of those. And then from the counts, we're going to order them in a descending order. And then I'm going to show you another little trick that we can do, but let me generate this first. So this shows us how many edits are coming from how many IP addresses. So you can decide whether you feel like these ones at the top are significant. I suppose maybe someone made some mistakes and quickly submitted in the short interval we were running this. They ran 4 different edits. Or maybe they were editing 4 different articles. This by itself isn't necessarily a problem, but you can see how it kind of gives you an idea of where you should pay attention if you are working on these edits. So why is this in 2 lines? So when I go to do the order by, I need a column, but this column is coming from the data frame that I'm producing by doing a .count over here. And so the problem is that if I want to chain this together, how do I describe that column? Right? It's not a member of a non-DF. It's a member of a derived data frame that's kind of in the middle of this expression. So there's no super easy way to name that column. So the first version here, I just did a perfectly reasonable thing, which is break it into 2 lines. Right? So once you've done the count, call that thing counts. And we could actually go in here if we wanted and look at the schema to see what's in there. So we can say a non-df.print schema. Right, so this guy looks like this. It doesn't have the counts column. And then we can go counts.print schema. Right, this has the count column, and there's no easy way to get at it when we're inline. Or is there, right? So this doesn't always work, but there is a helper function that will get you a solution to this many times. I don't want to say even most of the time, because it doesn't always work. But if you really want to put your operations in one long chain because it looks cool, or you feel like it may be easier to communicate what you're trying to do, there is a helper function called call. And what call will do is try and figure out if there is a column with this particular name in the current data frame, even if you don't have an external Python variable that points to that. So to chain this all together, I basically do exactly the same logic, but after I do count, I can then say order by, and I use the special call and give the name of the local column, the column that exists at this point but doesn't exist back here, and I can go like that. It'll give me the same output. It's just a neat trick that you can use when you want to refer to a column that didn't, you just don't have any name for the data frame that contains that column. And we get the same stuff. So some of the stuff in this lab is about visualization, and some of it's about data frames. But hopefully the streaming part is also a nice example. And the key pieces to take away from the streaming are that first we need to set up all the arrangements of our streaming graph before we start the stream. That we want to be a little bit careful about starting and stopping the stream, especially if we want to be able to recover a streaming application from failure. And that we can do operations on the D streams in many cases without ever dropping down to the RDD level. So if you look at this, you'll notice that the operations we do on the data are all on D streams. So we never actually had to go down to the level of working with individual RDDs. All of our maps and filters, they actually just work on the D stream. So not every piece of logic can be implemented that way, but it's nice to have that kind of higher level abstraction. I'm not going to do this other demo because we really don't have the time built in for that, but I wanted to give it to you in case you want to play with this later. There's one called log stream demo. This is a little more simplistic. But you can really, this one will let you actually just play with the knobs directly. You'll probably manage to crash or sort of break your Spark context at some point in here. That's okay. You can always restart your cluster. But here you can kind of drop down. This reads from a different server that spits out bogus log lines with some interesting jokes and stuff in there. But you can do things like filter for errors and warnings. So there's code in here that will do that. And you can experiment with things like for each RDD. So this is more for you to take home. There's also examples with windowing D streams. So if you want to create a D stream that represents wider intervals of time, you can take a look at that. And there's an example of reduce by key and window. So the D-stream thing is really awesome, but then as soon as you get back to the real world, you're like, wait a second, individual batches are not the resolution that I need to produce the reports from my streaming application. So in real life, you will need these stateful operations, either windowed streams or update state by key, reduce by key and window. And so I wanted to give you at least a couple of simple working examples of those. So you can try those out after the class if you want. This file is right here under today's labs, even though we're not going to do it in here today. So we have a little bit less than an hour left, and we're going to talk a tiny bit about machine learning. So first we spent a bunch of time on how Spark works internally. And then we looked at D-streams, and D-streams we said, well, okay, so there's a model for creating streams that adds some additional bells and whistles to the Spark core. Now with machine learning, we're really looking at APIs and libraries, right? So really nice implementations of algorithms for doing parallel machine learning, but there isn't anything special in the internals for this. There are some classes like vectors and so on, and matrices, but there's nothing really different about how Spark works for machine learning. So machine learning on Spark is just Spark, it's just Spark applications, but using APIs that are bundled together with Spark, so it's easy to work with. So we'll talk a little bit about machine learning in general, because I know there are a bunch of folks here that either don't use machine learning at all or haven't. So we'll talk a little about the sort of assumptions for what machine learning is about, and we'll talk a tiny bit about the coverage here, and then we'll look at a notebook that has a really nice detailed use of machine learning. So let's take a look here. So if you're doing ML, I apologize. The next 10 minutes are going to be really boring because you probably did this a long time ago. But for those who are new to it, this is kind of essential to making sense of the APIs because the APIs assume that you kind of have this stuff down. So we'll just talk a little bit about what machine learning is all about. So the idea is we might want to take some collection of data and we'd like to build some model that can figure out something about that data. So for example, we might have some log files, and the goal is to prioritize which log files are going to get our attention because we've got, billions of records or maybe millions of records coming through. So if we have something like this, oh, there's some test running and it's not really, has a warning maybe, but nothing interesting is going on, we want to downrank this or we want to make this sort of a lower priority. And if we have something that's got an error message where aliens are attacking, we'd like a system that can learn how to flag that as some kind of higher priority. So how do we do this? Well, we need to figure out how to come up with a model, and there's lots of different kinds of machine learning models. Then we need to get data to feed into the model. We need to kind of train the model and test it, and then we want to use that to do some scoring. So you can think of a model as being a function that takes some data, the stuff you're trying to analyze, and produces some kind of a label. So something that tells you something about the data. It could be predicting a price of something, it could be predicting a temperature, it could be predicting the value of a log entry for doing something like this. So that's going to be the output of our model. So the first thing we need to do is we need to take our incoming data and we need to featureize it, which basically means we need to convert it into some kind of numeric data that we can use with machine learning. And the way this is done in general, and especially in Spark, but also in other libraries, is that we're going to numerically featureize the incoming data, and there's lots of ways to do that. And then we're going to make that into a vector, and we're going to use those vectors to train our model. So one way to do this might be to do some word counts on here, right? Like how many times does the word running appear? How many times does the word test appear? That's one way to do it. So there's lots of ways to featureize different kinds of data, especially natural language data. So that's a whole discipline unto itself, and it's actually it's just as important as whatever algorithm you run, especially nowadays where there are so many great algorithms that are well understood, and we know that if the data has certain characteristics and it's featureized well, that we will get a nice model. If we run it, we get garbage. It's usually because we either don't have sensible data or we haven't featureized the data right. Right, so the ML models, they need something sensible to work with, things that can distinguish the incoming data in a meaningful way. So we're not going to spend too much time on how to do the featureization, especially for natural language, but there's a number of ways to do that. So things like TF-IDF, which do things like figure out the frequency of a term normalized for the frequency of the term in documents in a corpus. That's one way to do it. Just doing pure word counts is another way to do it. So there's lots of ways to do that. And so the idea is if we're doing, so there are a lot of different models and algorithms we might use. This is just an example to kind of illustrate the concept is if we have a linear regression model, what we're going to end up with is a bunch of coefficients that represent the weights applied to specific dimensions in our feature vector. Right, which sounds like a mouthful, but what you're doing is you're taking an input piece of data. It could be sensor data from a machine, or it could be a piece of text. You're creating it to a vector, right? So you're treating it as like an n-dimensional vector of, in this case, double precision numbers. And the linear regression model is that we've got a linear weighting that's going to apply to each of those dimensions. And so if we do the multiplication here, that we would end up with some kind of a score. And there's many different kind of models and different ways we can enhance the behavior of the models. But fundamentally, this is what we're doing, is we're trying to learn what these coefficients would be. Right? So in this case, the input in something like this would be to say, we have a bunch of training data. Here are the vectors that go with that. And for each of those training data items, we have a label as training data, because we already know whether it's important or not. So in this case, we've got a label for each vector, and we want to feed the label and the vector, a whole bunch of those, into the learning algorithm to build a model from those. And the model is going to be the particular model of this class, in this case linear regression, that best fits the data we gave it. Right? That's what the whole thing is all about. So when we do that, with all of the algorithms in Spark that work on labeled data, or supervised learning, this is called, meaning that we actually have scores for our data ahead of time, they're going to operate on RDDs of labeled points. So a labeled point is an object that contains a feature vector and a label. Right? This just means that we've got a feature vector and we know what the label is. The other category of learning is called unsupervised learning. That's where we have feature vectors, but we don't have the labels for them. So examples of those, the most popular one that you see are things like clustering algorithms like k-means, where we say we don't know the labels. What we'd like to do is take all the incoming data, and we'd like to build a model that separates those into n categories, where the n categories are sort of the most coherent. That is, we'd like the model that minimizes the error, the distance that points are from the category that they're associated to. So the unsupervised learning will take an RDD of just vectors. The supervised learning will take an RDD of labeled points. So that's what you're going to see labeled point everywhere. The cool thing about this is once you get used to this model, or this, I shouldn't use the word model, it's kind of overloaded here. Once you get used to this pattern, all of the different algorithms in Spark that use supervised learning will take a labeled point RDD. So you only have to sort of figure this out once, and then you can run lots of different kinds of training algorithms against this data using the same code. So we have our data, we've got our RDD of labeled points, and then we're going to feed this thing in. And we're hopefully going to get a model out that best fits our data. And once we have a model, we can use that to predict the label for future data. Right? So we have our training data, that gets us a model, and then we can use the model to predict values for other vectors that come through. Now we probably want some other steps in there, like we might want to validate our model by taking some other data that we didn't show it before and seeing how badly it does. And if it does badly, we might want to try the thing over again with some other parameters. So there's a whole process to this that's mostly about getting the parameters on the model algorithm right and getting your featureization vectors right in order to get something useful out of here. In this slide, we're talking about the same thing, but we've overlaid some terms that are part of the ML Pipelines API. So there's no new concepts here, but just to give you a correspondence for these labels, that when we're talking about the ML pipelines, that's the machine learning API that uses data frames, we call these algorithms estimators. We call the models transformers. So just to sort of set the terminology there. If we want to see how well a model did, there's a number of tests we can do, and those are called evaluators in the Pipelines API. So there's lots of different kinds of evaluators. In this example, we're looking at some kind of a metric, like for example, mean squared error, right? So what is the, what's the average squared error from the known data on the testing data? So we're going to look here just at an overview of what algorithms and elements are part of the Spark API. We're not going to look at programming them right in here. We're going to switch over to a notebook, and we'll actually run a real example. And we'll see this in action, because that makes more sense. So I'm going to skip over a couple of these slides for time purposes. We also have some nice slides in here that show some scalability and performance metrics. So these are not useful for understanding how Spark works, but they're useful for making the case of trying certain machine learning applications on Spark, or possibly making the investment to switch over from another system, or at least experiment here. So in terms of performance, so ALS stands for alternating least squares. That's a way of approximating a low-dimensional matrix, or approximating a large dimensional matrix with a lower dimensional matrix, so that you can figure out, in an example like this, product customer fit, or user product recommendations. This is a very common algorithm for that. So it's a known algorithm that's used all over outside of Spark. You can learn about that. The heavy-duty lifting in here is matrix factorization. But what we're looking at in this slide is the scaling, right? So if you look at Mahout, you can see that once we start getting into the significant number of millions of ratings, even around 100, 125 million, we really start taking up a lot more time to do this computation. Whereas with MLlib, we had somewhat better performance, it's vaguely linear-ish, in 1.2, and with improvements in 1.3, we have something that looks, at least to the eye, pretty linear, and it also scales a lot nicer than even the previous generation of the ALS in Spark. So, and especially when you compare, the time for the Mahout computation, say, to the MLlib version of the same thing, doing a lot of crunching for a lot less money. Here's another benchmark. Done on the Spotify recommendation data set. So 50 million users, 5 million songs, 50 billion ratings to work with. These iterations and rank are configurations to the algorithm. So there are some things called hyperparameters, basically parameters to the algorithm that it uses to build the model. That's what the 10 iterations and rank 10 are. Spend about 1 hour, and then based on the prices at that time on Amazon, this cost about $10. So crunching quite a lot of data in a pretty reasonable way out in the cloud. So we're not going to drill way down into the details here, but to give an overview of the algorithms that are supported, these are the categories of APIs. These are not specific APIs. So things like classification algorithms, regression algorithms, linear algebra functions, and so on. And then we've got some lists that summarize the APIs underneath there. So within the realm of classification, we have things like logistic regression, which for sort of splitting things into two categories, linear support vector machines, decision trees, random forests, and so on. We've got a whole set of regression algorithms. These functions here or packages here are for featurizing, right? So these are not for doing the modeling themselves. They're for getting from your raw data into some kind of useful set of features, which is, like I said, that's oftentimes, the harder part of the machine learning process is figuring out how to get proper data to train on. And so there's a lot of helper functions in here for transforming your data into vectors that are hopefully useful. So some of these are natural language related, some of these are numeric. We've got discrete cosine transform. I think that's newish to get some signal processing type stuff in here. Again, summary of additional algorithms. So I don't want to read you a slide full of APIs, but this is a nice thing to be able to take back and give you an overview without pouring through the docs of what's built in. It's also worth mentioning that let's say you've either read about or researched some interesting algorithms, you'd like to try them on Spark, and they're not in here. right? So the answer is not necessarily just wait until it shows up in Spark. Look out on the internet, look in Spark packages. There are a lot of companies that have built implementations of other machine learning algorithms that are not incorporated into the core Spark distribution. So I don't know what the numbers are like for every one of these algorithms. I'm not sure how many really high quality other ones are out there, but there's definitely a lot. So I think there's only one, for example, like neural networks, I think there's only one neural net implementation in Spark at this point, but I know that there's a whole bunch of them that other people have written, and some of them have been used really successfully at large companies. So definitely look out into the community at pulling in some of those if you want to try them out. Some of the current focus is integrating with Spark R, so basically making it easier to use existing R approaches, more integrating with pipelines and data frames, so being able to not just take really simple flows like load data, extract features, train and evaluate, but more complicated ones. So being able to create pipelines that take different data sources, transform and combine the features, train more than one model, and can create more sophisticated output. I'll give you a notebook that we're not going to do in here, but you can take a look at it that's really nicely done that gives an example of a lot of this ML pipeline stuff. It's not too complex, and it's really excellently documented. It's part of the Databricks guide. So this is just a little bit of the roadmap. Definitely take a look at the JIRA. So that's all public. You can look at that, and you can also look at the mailing lists and see. So this is this sort of is the bucket for 1.6, but I'm not totally sure what will end up in there. So I'm gonna sort of stop there with the overview of machine learning, because this is just that was meant to just basically give you an idea of what the machine learning conceptually is about. Roughly give you a resource to go to about what's in Spark. I mean, like I said, we just looked at a bunch of slides. I don't expect you to remember which ones are where, but it gives you a place to go look. And what I'd like to do is spend some time looking at actual code, and we can run through a nice example. So I'm going to come over here. Now, the first thing I want to do, just because at the end of the day I know some people may be needing to head out or something like that, is I'm going to find you that other example that we're not going to do. So under Databricks Guide, there is one called Power Plant Pipeline. So I'm just going to make a copy of this so you don't lose track of it. If you're interested in the ML pipelines and the Spark ML API, definitely look at this. That's a nice example. So that will show up in here. What we're going to do is we're going to go through an example using MLlib. So we're not going to be using data frames or pipelines for this example. And this is actually not based on Wikipedia. This is based on a data set that you may have seen in the R world. So in R, or at least when you pull in the graphing package with R, you get a data set called diamonds. It's a bunch of dimensions, costs, and sizes for diamonds. And what we can do is we can look at how we would analyze that data set and train up a model on that. So what we're going to do is we basically want to load up the data. We want to look at the data to figure out what the characteristics are and how we might featureize it. Oh, I didn't really copy this. I guess I should copy this. I guess everyone should copy it. So I'm going to go ahead and clone it so we're not all in the same place. So I'm not going to make any alterations to this. There are no exercises in here. We're just going to take a look and sort of work our way through this code. So we want to understand the data. We want to split the data up into training and test sets, right? Because if we train on data, it's hard to figure out how well that model does if we don't have any test data, right? If we train on a set of data and then we start applying this to new data, it's very difficult to figure out how good our model is. So what we want to do is systematically split up our data, train on one chunk of data, and then evaluate on a different set so we can see how well we did. And that will allow us to tune our modeling. So we want to do some splitting up of the data. We're going to featureize our data. So that includes things like we have numeric features that we can use for almost any kind of modeling, things like dimensions of a diamond. But we've also got qualitative or categorical features, things like the clarity of a diamond, where there's like 5 or 6 different levels. So these need to be converted into something that's appropriate for the algorithm we're using. And so there's approaches to that. So we'll look at that. We'll train a model. We'll do a decision tree here. And with the decision tree, one of the parameters that we can control, these so-called hyperparameters, is the depth of the tree, the complexity of the tree that we're going to allow the algorithm to build. So we're going to look at a bunch of different depths and figure out which ones produce more errors and which ones produce less errors. And we'll also look at how we can ask Spark to show us the internals of the model. Like, tell us what you figured out, and we could use that to understand how it works. So we'll start right over here where we're going to pull in I'm going to attach this to my cluster. We're going to pull in a CSV file with the diamonds data. And if we do a take 5 on this, and this is just an RDD, so this is an RDD of strings here. So it looks like we've got maybe some column headers. That's what this looks like. And then we've got something. This looks like maybe the index of the element in the data set. This 1, 2, 3, 4 looks like it's probably not a feature of the diamond. It's probably a feature of the row here. And then we've got values like 0.23 carats and ideal cut and color E and so on. So let's go ahead and get rid of the header and split these things up into individual properties. So we're going to go and strip and split on the commas, and we're also going to do this. So this is a filter that should basically allow everything through except the first line that has the column headers that says caret. Now we're going to map these over to a bunch of floats, except for the qualitative ones, these things like ideal cut, right, or color E. So those we're going to keep the original ones. And then we're going to convert to a data frame. So once we've got that, we'll make a data frame with these column names. And it's going to look something like this. So let's print the schema. Okay, well this makes sense, right? Because we took the data and we cast to floats for all of these guys, and the qualitative parameters or categorical ones we left as strings, right? So this, we're getting out pretty much what we put in. In this case, we're cheating. In real life, you often have data that has all kinds of problems in it, so there's a whole other art to data cleansing, which we're able to skip here because we're working with a data set that's reasonably small and is actually sort of clean and well known. We can make a pretty version of the table and see what a few of these rows look like. Right, so this is what it looks like once we've parsed it and loaded it in. This is similar to the stuff we did this morning using Wikipedia. So far we haven't done any machine learning, anything at all. We've just arranged a data frame with the right types. And now what we want to do is take a look at these categorical features, right? These are the ones that are not sort of on a continuous numeric spectrum. So let's go and look at what the distribution of values look like in here. So here we've hand-coded the names of those properties, and then we're going to go and do a select on those, a distinct, and pull them together. So we can see what is the range of property values in our data set for these. Right, so for cut, we've got 6 different values that appear in the data set, and then 7 here for color, and looks like about 8 or so for clarity. So we've got to figure out some way to convert these to numbers because none of the algorithms that we have can do anything with them the way they are. So one thing that's useful to look at is to look at the distribution of some of these. So if we come over here and say pull out the cut data, we can look at how that's distributed. So okay, we've got kind of an interesting distribution here. Now we can do the same thing for a continuous property like carat, right? That's a weight measurement, so it's kind of a naturally continuous variable. And it looks like, well, it's kind of crunched down here. Let's see if we can make this a little bit bigger. Extend this out. So, well, it looks like we don't have sort of a totally normal distribution here. We've got something that's bunched up against 0, which is a relatively common thing when you have sort of a lower bound like this. There are mathematical operations we can do to transform these. So some algorithms train poorly on distributions like this and might train much better on a distribution that looks different, like maybe a regular normal distribution. So part of the art of manipulating the data before doing the training is to look at things like that and do some of these transformations. Here we don't really have to worry about it, but this is why we would want to look at the distributions here and figure out, try and understand really what they represent and how they're arranged before we throw them at the algorithm. Because you'll see that when we get to the ML part, it's like 2 lines of code. So there's no programming to do to train the ML model, and to do a prediction off of it is like a line of code. So there's no coding for that. It's all about garbage in, garbage out versus having something meaningful. So really the work is, when we have nice implementations like we've got in Spark, there's not much to code there. The work is trying to feed in meaningful things and figuring out how to tune the model. So okay, so we've got this arrangement of data, and now what we want to do is start to actually featureize this. So we're going to bring in some helper classes, vectors here, and labeled point. And we're going to pull out the price column here. And the price column that's our label. What we're going to try to do here is predict a diamond's price or sale price based on its other characteristics. So the price is the label. When we're training, that's the label we're going to put alongside our feature vectors. And when we predict, we're going to assume that we don't have a price. We're trying to predict the price from the rest of the parameters. So we're going to separate this out over here. And that will give us features that look like this. And then the price becomes the label. Now the next thing we need to do is deal with these categorical or qualitative columns. So these need to be converted to numbers in some sort of pattern. So what we can do is build a little dictionary to help. We can actually come in here and let's just print this out and take a look at what it looks like. So if I go print category indexes. So what we've done here, it's just Python code really, but what we've done here is created a map where for each of these properties, we've got a mapping of the string value for that property into a set of integers. So there's a bunch of ways to deal with those kind of columns. So for a decision tree, this works out fine. Another thing you'll see a lot of is called one hot or one of k encoding. So if you have a parameter that can take 5 values, instead of calling it 0, 1, 2, 3, or 4, you'll actually create 5 different features, which are all 0 except for the present value, which you'll switch to 1. So that's another pattern you'll see a lot of, and there's helpers in Spark to do those conversions. Now what we want to do is we want to go ahead and assemble our feature vectors by pulling all of these things together. So let's go ahead and run this here. So we'll make up our vectors. We're going to plug in our different columns. We're going to plug in the categorical columns, basically reading out of this dictionary we just built. So this is really some Python data manipulation. And we can kind of spy on this and see what it looks like. So if we do something like indexed features dot show. Oh, we can do like a take. You can just see what this looks like. Or maybe not. See, did I actually run this?
I think you forgot to import all this stuff.
Did I forget to import stuff? Well, that would be, oh yeah, I think I may have forgotten to import stuff. Thank you. Let's see if that helps. Ah, there we go. Thank you. Much appreciated. Okay, so here we've got this is what the vector looks like after we've basically just, all we've done is pulled together the numbers we already had. So the continuous features are just being copied into the appropriate place in the vector. The categorical features are being looked up in their little lookup table and plugged into the right place. And then the prices are pulling out the label columns. So that's what we're going to have in the diamond prices. And now what we're going to do is make our labeled points, right? So remember, a labeled point is a label together with a feature vector. So we're going to take our prices and we're going to zip it together with indexed features, and that will produce our, we'll take that, we'll get a pair, so we'll do a map from the pair to a labeled point constructed on the first part of the pair, which is the price or the label, and the second part of the pair, which is the feature vector, and we'll take a look at that. So we'll count those, and we'll also look at what a couple of them look like. So this shouldn't be too surprising, but if we go into indexed diamonds, and we do like a take 4, what do we expect to see? A price and a vector in each one, right? So that's what we've got: labeled point, price, vector, labeled point, price, vector, and so on. So just so we can keep track in our minds of what this looks like. Now we need to do our splitting, right? Because if we train on all of our data, besides the fact that it'll be really hard to evaluate, we're going to have trouble avoiding things like overfitting, right? We'll get a model that's really, really well tuned to the data we gave it, and whether that has anything to do with the data in the real world, we don't know. So we're going to go and split this up using a helper method called random split. So we'll use a nice Python destructuring kind of thing here and grab training data and test data as 70% and 30% of our data, and then we'll set those to cache, and we'll do a count on them. Why are we doing the count? Well, just to force them into the cache. So we're just running a job so that these guys end up cached. And now we'll go ahead and train a model. So we're going to import the decision tree and decision tree model types. And we're going to give the decision tree a hint here. So the decision tree will work better if we can tell it which parameters are categorical versus which ones are continuous. So it can save some work there. And now here's the actual training, right? So like I said, when we get down to actually building the model, it's one line of code. Decision tree.train. We feed in the training data, and then this is just that hint. It's the collection of categorical features. So if we run this, we get out decision tree model regressor of depth 5 with 63 nodes. Well, is it any good? Who knows? But we've just trained a model. So now let's go and figure out how well or how badly it does. So since we held out some data, we can go and do some testing. So we can do things like calculate the root mean squared error. So the nice thing about root mean squared error is that the units for that are the same as the units of your label, right? So if we are using price as our label in, say, euros or dollars, then we would expect to see the error here in euros or dollars also. So here we've got a sort of a brute force calculation of root mean square using NumPy. And we can go run that, and we see that the initial training error was 1,000 units, euros, dollars, whatever you prefer. And is that any good? Well, we don't know. I guess it depends on the price of the diamonds. If the diamonds are $500,000 each, this is pretty nice. If the diamonds are $250 each, this is chaos, right? So we don't actually know if this is good just yet, but we can figure out how to measure that. But we do know that the lower the error, the better the model, right? Regardless, right? In absolute numbers. So let's see if we can tune this model by creating a number of different models using different hyperparameters or different configuration parameters. And we'll see if some of those produce better models than others. So what we're going to do is we're going to create a collection of parameters that we want to try. So this process is sometimes referred to as hyperparameter search or hyperparameter grid search. And the reason for that is that for each parameter, like this, we have a bunch of values. So if you think about having several parameters you can tune and several values for each, then in each of the squares on that kind of matrix, that represents a different model off of the same data, right? So what you'd like to do is create all those models or search that in some intelligent way, maybe if it's a really big grid, and figure out which models are going to be better. Right? In the case of max depth, we expect to have some kind of a curve, because if the max depth is 1 or 2, we're not going to get very good data. And we know that with a decision tree, if we crank max depth up enough, it'll perfectly overfit our data. Right? There'll be a branch at the end of the tree for every single input point. Right? So then we'll have complete overfitting, and it'll do disastrously when we give it other data. So we expect to see some kind of a curve that starts out bad, somewhere in here gets better, and if these numbers get high enough for depth, it starts to get bad again. So let's see if we can do that. So we're going to cache some more data here. And so here we're actually doing this search manually. So the Pipelines API has some automated ways to tell the system about your parameters and how you'd like to search. Here we're doing this by brute force, right? We're doing a map, a regular old Python map, where we're saying, okay, for each of the max depths, build me a tree that uses that max depth, right? And I'm going to get a collection of trees out of this thing. So that's what I've got here. And we can take a look at what these look like by calling toDebug string on the trees, right? So here's what the decision tree with depth 1 looks like. So feature 0 was the only one that it chose to use. If it's less than 0.99, it's 1,627 euros. And if it's more than 0.99, it's 8,000 euros. And that's the end of it. So OK, so there's our model. So here's a slightly better one. This has depth 2, so it can provide a little more resolution. So that's just what it looks like if we dump out some of the data. And one of the nice things about decision trees, they're easy to understand. So some of these models can be quite a bit harder to figure out what the heck they actually mean. But most of the model, possibly all of the model APIs, will give you a way to export what it's the key values that the model's based on, whether they're obviously intelligible or not. So let's go and calculate the errors across all of these trees. Right? So this is Python map, not Spark map that we're running here. And we're just saying for all the trees, calculate the error. So let's take a look and plot those. So we can bring in matplotlib, and if that's a tool that you've used before, you can bring it right in here, and we can generate some charts.
So where do those run?
So where do, which parts?
The map.
This map is running on the driver, but each task within the map runs on Spark. So this is a Python map that's just happening in the driver, and it's basically saying for each one, create a model. The algorithm that creates the model runs distributed. And so that's how it's basically like a for loop, really. It's a glorified for loop in the driver. And if we chart those, we can see the training error just goes down and down. That's what we expected, right? The more depth you get on the training data, you get better and better until eventually you're perfect for the training data. When we do the validation, we notice that the validation gets good somewhere around here, and then it seems like it either stays the same or maybe even gets worse, right? And that's also what we expected, was to find some spot in here that's kind of the optimal for this parameter. So here we're just asking NumPy to find us the smallest, the parameter value that corresponds to the smallest error, and it's the same one that looked reasonable to our eyes, which is a max depth of 10. So, well, now that we figured that out, let's go back and try to get a better model. Well, how can we do that? We can train using this best max depth, but across all the training data. So let's go ahead and do that. And again, the training call here, it's just the one line of code. So it's leveraging the algorithm that's already implemented in Spark. And so we get out this model here. So now the question is, well, now we've got a final model. How well does that do? So we would hope that it maybe does a little bit better than the one we saw before, but we're not 100% sure about this, so let's just take a look. So the final model has 594 units on the training error, 665 on the test. So this is way better than the first model. Remember, the first pass we made through this was like 1,000 or so. So by doing the parameter tuning and the cross-validation, we were able to get, in absolute numbers, we got our error way down. Now, that still leaves the question of, well, is that meaningful, right? Because again, it's like if the diamonds are $25 each, then the first one stunk and the second one stinks. If the diamonds are, sufficiently expensive, then these start to look both pretty good. So we'll see how this works compared to the original one, right? So there's the final error versus the initial model error. And now we can make trees from the full data set and see how they score here. Okay, so on the full data set, it looks like we're still doing pretty good in here, and our final test error is not that much worse than the training error. So it's all looking pretty reasonable with this model, at least given the options we've got. So we talked a little bit about the root mean square error. And we said that, well, it depends how that particular number depends on the value of the diamonds themselves. So the absolute number is not as useful as knowing sort of what's the error as a rate or as a proportion of the quantity we're trying to predict. So that's what's going on in this last chunk of script here. Is we're going to make another chart, but we're going to calculate the relative error. So how big is the error compared to the quantity we're trying to estimate? So this is roughly the same shape picture, but what we're doing here is calculating the relative error relative to the price. So it looks like our final results here are somewhere around 0.1 or 10% of the price. So depending on your business application, that may be a pretty reasonable thing. There's no total answer to that. Depends what you're trying to do, but it's not ridiculous, right? We certainly could have ridiculous error rates, and this one isn't ridiculous. Right, so our final predictions are within about 10% of the selling price. So that's pretty nice. And if we wanted to understand a little more about what our model derived, we could do a debug string on that, and we'll get a big printout of the tree. So what can we learn from looking at the big printout of the tree? Well, one of the things we can do is we can look at which dimensions of our data had the most influence in the tree. A lot of times the ones that percolate to the top, the ones that are some of the first decisions, those are ones that have a large influence in the prediction. So we can see that we've got features 0 and 6 coming up a lot near the top. So that's the first and 7th features. This is feature 7 and 0. We're getting features 6 and 0 here. Remember, there's random selection involved, so that may be why we have something a little bit different. And we can go back to our original data and say, well, what are those columns? So we've got the y dimension and the number of carats. So we can do a sanity check there and say, well, yeah, it's reasonable, right? The size of the diamond and the weight of the diamond probably have a pretty big influence on the price of it. So those seem reasonable. And then there's a little, we can print out another decision tree and kind of look at what shows up in here. So for example, a different one of the trees, all the decisions are made purely on dimensions 0 and 7. So that's kind of interesting. So there's lots of ways to do that. If you take a look at the power plant notebook, the APIs used there are a bit different because that uses the ML Pipelines API. So they're working with data frames not just for sort of visual convenience, but actually as the mechanism for running data through the algorithms. And in that version, they actually do a couple different kinds of models. So there's, I think, a linear regression model in there and a tree model in there. And so you can see two totally different kinds of models and see how they perform. But hopefully this makes some reasonable amount of sense, and you can see that actually generating a model and evaluating it are pretty easy to do once you've got some set of data to work with. So that's pretty much all the material that I was going to present here today, and we're doing pretty well on time because I was hoping to end at 4:50 and it's like 4:52. So I think what we'll do is we can do miscellaneous questions, and we'll have some time for that. So if anybody has, I know there were a lot of questions earlier where I said, well, we'll come back to that either later in the class or at the end of the day. So if there are questions I haven't talked about it or haven't answered, we can chat about that stuff. Yeah?
There was a question before regarding the UDF compared with the NAP RDD. How does that perform? Like the same type of performance, or the NAP RDD performs better? You have to do like a UDF on that frame. How does it compare to the same kind of operation function on RDD in a NAP form?
So it should, if the languages are the same, we should get comparable performance. So there was one question was like the tax from running a function that has to run in Python versus say a UDF that's in Scala or Java that runs completely. So there is going to be overhead if you have to switch out to Python to run that code. If it's in the same language, so Python UDF versus an RDD.map on Python, or same thing where they're both in Scala. I don't have benchmark numbers, but that you should get similar results. There shouldn't be a substantial tax at all to doing the UDFs. Yeah, absolutely. And actually, well, I guess we're not gonna use this part for the recordings. I was gonna see if I can get you a microphone, but it doesn't matter because I don't think we're gonna put this in the recording just because it's not always as useful for people that are not here.
So to avoid a watch shuffle, that's what I call it, can you do a broadcast? So just bring like, for example, like a dot frame into each single partition, just to avoid the shuffling. Would that be like a good strategy at all? So for one understanding, if I'm trying to do a join between two partitions, they get a little light in shuffle.
Oh,
So
yeah.
you can avoid that just by bringing everything into one partition and then broadcasting that data frame into each single partition of the other.
So it wouldn't be per individual partition, but the short answer is yes. You can take a data set and you can, rather than join against it using a shuffle, you can broadcast it.
So that should be good performance, right?
It depends on the size. So the threshold, the default threshold for that is something like 20 megs, and I think you can tune that. It depends on the size, because if the thing you're broadcasting is sufficiently large, then you're gonna have a problem, because that whole entire thing needs to fit into the memory in each of the executors and in the driver if you're building it up in the driver. So that's sort of the constraint.
Is that something that Catalyst does automatically, or is something that?
Yeah, Catalyst will automatically choose to use the broadcast join when the thing you're joining is below that threshold. The RDD API won't, so you'd have to do something differently there. But with Catalyst it will, and I think you can tune that threshold of the 20. I think the default is something like 20 megabytes. But the idea is that if that gets sufficiently large, it also becomes less efficient. So it may not be worth it. But that's what you're describing is a really common thing. Is you have like a lookup table, maybe business rules or customers, cities, locations. These things that are only a few megabytes, but you don't want to always be doing joins across the whole thing. That's a perfect use for this API called broadcast variables. You get those things out there, and then you can use those values in the lambdas that are running out on the cluster without having to do a proper join on them. Yeah.
Say that there is a pipe, you can use pipe to run binaries.
Ah, yes. Yeah.
This is a nice way to integrate all the applications or C++ applications. But I haven't seen anything to distribute the binaries on the nodes for where the code is actually executed. So is there a way to do that? So we can write Python script that run C++ binary through pipe, but we have to distribute the binary on the nodes that actually execute the code.
Well, so one way to sort of fake it is if you're using a shared file system, right? Then all the nodes can see it, or to have all of the nodes, you have some other script that retrieves it for all of the nodes. That's kind of cheating, right? To be honest, I don't know the answer canonically for that. I think that with the yarn, when you're running on yarn, I think there's a way to distribute those so that at least it's not your actual external script, but at least libraries are available. Because it's the same way that you would distribute libraries that you're using for the Python code that you're running through Spark. As far as the other executables, I'm not sure that would get you there. And then I think on Mesos, it's a whole different ball game. So I guess the short answer is I don't know of an automagic easy way to do it, but I also don't claim to know exact. I haven't spent too much time trying to solve that exact problem. Sorry.
Do you know where I can ask this question?
Well, you could. I would say to like you could definitely ask it on the mailing lists to the extent that because this is sort of on the border of, is it part of Spark or is it really part of the cluster environment? So this is something that, if you look at the docs for the specific cluster deployments like Spark on Mesa, Spark on Yarn, to see if there's helpers there. Those would be the places to do that. But this just might be an operational scripting thing that you might just need to do. The hotter it gets later in the day, the harder it is to focus on any kind of questions. Well, if there are any questions, I'll hang out here. So if anybody wants to talk to me in like a less sort of formal environment of me standing up here, I'll hang out and we can chat about anything that you like. So thank you very much. And I hope the rest of the conference, that's a great place to ask anything that we didn't get to today. And I hope you can figure out a lot more awesome Spark stuff over the next couple of days.